The sky is nearly uniform at the larger scales, a faint wash of ancient microwave light, and a sparse sprinkling of foreground stars, but nested within this quiet field lies the observational edge, where the first known galaxies come into view as small red smudges stretched by the expansion of space. At this outer frame sits GN-Z11, a compact system observed at an extreme redshift that places it within the first few 100 million years after the beginning, when the universe is less than 1/20th of its present age. Its light has crossed nearly the entire observable reach, travelling for more than 13 billion years through changing conditions as matter-thin structures grow and the intergalactic medium slowly clears. The detection rests on the simple fact that space expands, and with it the wavelengths of photons. Features that originate in the ultraviolet arrive in the infrared, and narrow spectral breaks that mark neutral hydrogen become broad steps that instruments can isolate. To set the frame with care, the map begins with distance as light travel time brightness, as flux dimmed by geometry and expansion, and colour as a record of how strongly wavelengths are stretched between emission and detection. The result is not a portrait in detail, but a resolved presence, a small galaxy whose signal sits just above the threshold, where a background fluctuation could masquerade as a source, yet repeats when the same sky is measured again with deeper exposures and finer sampling. At this range, the universe behaves as a lens that smooths and dims. Surface brightness falls rapidly with redshift because each photon loses energy to stretching, and because the apparent area over which emission spreads grows with distance. The contrast between source and sky is low. The background from zodiacal light and diffuse emission in the instruments dominates raw frames. To reach the edge, long integration stack countless short exposures reject cosmic rays and subtract artifacts with masks built from repeated visits to the same field. The outer frame is thus as much a product of patient method as it is of cosmic scale dithered imaging, to sample the point spread function, careful flat fielding to stabilize sensitivity across detectors, and a sequence of filters chosen to bracket the spectral break that marks when hydrogen absorbs light blueward of a specific transition. The source survives this process because it obeys consistent rules. It vanishes in bluer bands where absorption should be strong, appears in redder bands where absorption should be weak, and maintains a shape that matches the instrument's resolution, rather than the irregular footprint of noise. Placing GN-Z11 in this frame also means keeping separate the three distances that observers use. Light travel time gives the age of the signal a measure in billions of years that anchors the narrative in cosmic history. Angular diameter distance turns measured angles into physical sizes at the epoch of emission, a quantity that shrinks with redshift until a peak, and then grows, so a fixed angle can correspond to a compact physical object in the early universe. Luminosity distance scales flux to intrinsic power climbing steeply with redshift, and making early galaxies appear faint even when they form stars at vigorous rates relative to their small masses. These distances connect what the detector sees to what the galaxy is, but in this outer section the emphasis remains on the path rather than the source, a photon field stretched by expansion, a geometry that dilutes surface brightness, and a set of filters that convert these facts into selection criteria. The observational edge is not just faint, it is selective. The method relies on a break in the spectrum caused by neutral hydrogen that absorbs photons above a specific energy. In practice, this appears as a sharp drop between neighbouring filters for objects at the right redshift. Candidates that meet this colour criterion are then tested against contaminants, cool dwarf stars in the Milky Way with similar colours, dusty galaxies at intermediate distances whose reddening can mimic a break and noise peaks that pass thresholds by chance. The culling uses morphology because stars are point-like at these resolutions, while distant galaxies can be marginally extended. It uses additional bands to confirm the absence of flux where the break should be, and it repeats measurements with independent instruments where possible. The outer frame asserts only that GN-Z11 survives these tests robustly enough to be considered a real high redshift galaxy, and that its placement near the edge follows from the consistent alignment of colour morphology and reobservation. At such early times, the universe is compact and lines of sight intersect a web that is only beginning to show contrast. The cosmic microwave background has long cooled into near uniformity, but the intergalactic medium retains significant neutral hydrogen in patches. Light from the earliest galaxies must thread these patches, and in doing so, the photons blue ward of the hydrogen break are scattered out of the line of sight, strengthening the signature that selection uses. The same medium can slightly lend sources, magnifying or demagnifying them by small factors that carry substantial weight when flux is near the limit of detection. The field around GN-Z11 is therefore evaluated for foreground structures that could distort fluxes, and the absence of strong lensing features in most frames keeps the interpretation straightforward, a bright compact source at high redshift rather than a strongly magnified, intrinsically fainter system. The telescopes that operate at this edge are designed for stability and sensitivity in the infrared, where redshift pushes most features from the rest frame ultraviolet. Large cold mirrors minimize thermal emission that would overwhelm faint signals. Detectors are tuned to low noise and are read out with patterns that allow cosmic ray rejection and persistence control. Guiders keep pointing steady to fractions of a pixel over long series. The spacecraft orbits place instruments above the atmosphere, removing absorption bands and air glow that on the ground would swallow the very wavelengths where the earliest galaxies appear. The outer frame is thus a partnership between cosmic conditions that move light into the infrared and engineering that holds a telescope still and cold long enough to catch it. GN-Z11 stands at the confluence, a source bright enough intrinsically to rise above the floor, and an instrument stable enough to register it. Even at this scale, caution remains a part of the frame. Photometric redshifts derived from colours carry uncertainties and degeneracies that only spectra can fully resolve. Noise correlations in processed images can inflate significance if not modelled. Background subtraction can remove real low surface brightness wings if too aggressive. The outer frame acknowledges these limits and keeps claims within what the data support. GN-Z11 enters as a compact high redshift galaxy candidate whose colour and brightness are consistent across instruments and reductions, whose morphology is stable, and whose placement near the edge follows from the strength of the spectral break and the absence of flux at bluer wavelengths. Later sections will move inward to the confirmation and to the physical interpretation, but the outer field sets the constraints. Faint fluxes measured repeatedly colours that match expectations for early galaxies, passing through a neutral medium and an angular size that is small yet resolved enough to differ from a point source. Cosmic variance also touches the outer frame. The earliest galaxies do not distribute uniformly across small fields. They cluster along filaments, leaving some deep images richer and others poorer. A single detection does not measure a global abundance. It demonstrates possibility and sets a benchmark for brightness and size at the edge. The field around GN-Z11 is read for neighbours at similar colours and for hints of structure that might signal an early group or proto-cluster. At this stage, the map remains sparse, but even sparsity supplies context and individual source in a regime where small number statistics prevail, and where each detection adds a point to the curve that later surveys will fill. Finally, the outer frame fixes language and units to avoid confusion in what follows. Ages are written in billions or hundreds of millions of years, not in symbols. Distances are described by light travel time when the goal is historical placement, and by physical size at emission when the goal is proportion. Temperatures surface, brightnesses and star formation rates will appear later with units spelled out. Proper nouns are capitalized to separate instruments and epochs from generic terms. No metaphors substitute for statements about gas stars and radiation fields. The aim is to keep the boundary conditions of observation clear before moving inward to the measurements that assign a precise redshift, the physical dimensions implied by the angular size, and the constraints on stellar populations and interstellar media that colour and spectra provide. Within this carefully drawn perimeter, GN-Z11 stands as an object seen near the limit, where the early universe becomes accessible to direct imaging. Its presence is secured by repeated banded measurements that identify a strong spectral break and a consistent infrared flux. Its placement is constrained by the geometry and dimming that the expansion imposes, and its context is the sparse high redshift sky, where each source must be weighed against contaminants with patient methods. The outer frame holds here with the edge of observation described as a set of processes that turn faint light into a catalogued object, and that separate a real early galaxy from noise peaks and local stars. The next step moves one layer inward, staying with the same steady voice to the light itself as a timeline. How a photon field stretched by expansion carries information about when the source formed, and how long its journey has been, and how those times translate into an epoch when the first generations of stars begin to assemble small galaxies within the growing scaffolds of dark matter. Light from GN-Z11 begins as ultraviolet radiation from hot young stars and from gas heated by their short lives. As space expands, each photon's wavelength stretches by a factor set by the scale of the universe at emission compared with the scale now. This stretching is measured as redshift. High redshift does not only mean far away, it also means early in time because light takes time to travel. The look-back time to GN-Z11 is more than 13 billion years, placing the emission within the first few 100 million years after the beginning, when the universe is less than 1/20th of its current age. In this regime, distances carry specific meanings. Comoving distance fixes the separation on the expanding grid that rides with the flow. It remains constant for objects moving with the general expansion. Luminosity distance is the factor that turns observed flux into emitted power. It rises steeply with redshift because photons are both fewer per unit time and lower in energy by the time they arrive. Angular diameter distance turns angles into sizes at the time of emission. At extreme redshift, it reaches a maximum and then declines. So a galaxy at very early times can appear with an angular size that corresponds to a surprisingly small physical extent. GN-Z11 lies across these definitions in a way that turns faint infrared light into a timeline and a size. The key observational marker at this epoch is the hydrogen break. Neutral hydrogen in the interstellar medium of a galaxy, and in the intergalactic medium between galaxies, absorbs photons above a specific energy threshold, set by the binding energy of hydrogen's ground state. In rest frame ultraviolet light, this creates a sharp drop shortward of a particular wavelength. Expansion shifts that drop into much longer wavelengths by the time the light arrives. In broadband imaging, the source is absent or extremely faint in filters that sample the blue side of the shifted break, and appears in redder filters. This pattern is used to select high redshift candidates. For GN-Z11, the strength of the break combined with faint but repeatable detections in redder bands marks the light as originating in the early epoch when the intergalactic medium still contains significant neutral hydrogen. Spectroscopy then refines this picture by resolving the slope and by looking for the damping wing that neutral hydrogen can imprint on the red side of the break. Even when features are weak, the overall shape of the continuum carries the signature of a high redshift source crossing a partly neutral medium. The same expansion that stretches light also alters the apparent pace of time near the source. Processes in GN-Z11, such as bursts of star formation or changes in hot gas output, unfold in the galaxy's proper time, but observers see them slowed by the stretch factor. This time dilation means that variability is damped and that measurements over months or years in the observer frame sample shorter intervals in the galaxy frame by a factor equal to 1 plus the redshift. For a system at extreme redshift, this factor is large, so the observed scene is a time-averaged view. That average smooths fluctuations in star formation and makes the spectral energy distribution more stable for classification, which helps when signals are faint. It also warns that short episodes in the galaxy's life can be hidden inside what appears as steady light. The light path to the present is not empty. At early times, the intergalactic medium contains islands of neutral gas that scatter ultraviolet photons out of the line of sight. This absorption builds the trough blue ward of the break and strengthens the selection. As reionization proceeds, ultraviolet radiation from early stars and from accreting black holes ionizes larger volumes, lowering the neutral fraction and allowing more photons to pass unimpeded. GN-Z11 sits close to this boundary. Its continuum shape and any line emission that survives tell whether its local environment is already ionized or still partly neutral. In many cases, bright emission lines from hydrogen are reduced or absent at the highest redshifts because neutral hydrogen in the surrounding medium scatters those photons. A detected line would suggest an ionized bubble around the galaxy, while a smooth continuum with a deep break suggests a more neutral environment. Either outcome is compatible with the patchy nature of reionization. The key is that light carries information about both the galaxy and its cosmic neighborhood. Because surface brightness dims strongly with redshift, the outer parts of a small early galaxy drop below detection first. What remains visible is a compact core where star formation is most intense, or where stellar density is highest. Angular sizes measured in the infrared filters that detect GN-Z11 therefore provide a lower bound on its physical extent. Correcting for the instrument's point spread function reveals a half-light radius of only a few hundred to a few thousand light-years at emission, depending on the exact profile assumed. Such sizes are far smaller than those of present-day large disk galaxies, as expected for systems still assembling their mass. The light profile often matches a simple, centrally concentrated form consistent with a nascent bulge or clumps of vigorous star formation rather than a settled disk. Colours across the infrared bands locate the slope of the rest frame ultraviolet continuum. That slope is sensitive to dust and to the typical temperature of the young stars. A very blue slope suggests low dust content and hot, massive stars, which fits expectations for a young system in a low metallicity environment. A redder slope could imply dust reddening or an older stellar population. For GN-Z11, the observed slope is commonly interpreted as relatively blue, aligning with rapid recent star formation and low dust. This is consistent with the idea that early galaxies have not yet built large dust reservoirs, because heavy elements and dust grains form in earlier generations of stars, and in supernova ejecta, which require time to accumulate. Light across these bands also constrains the specific star formation rate, the rate divided by the stellar mass, which tends to be high in early galaxies, as gas fractions are large and cooling times are short in dense halos. Translating flux into star formation rate requires assumptions about the initial mass function of stars and about how many ultraviolet photons are produced per unit of ongoing star formation. In the early universe, the initial mass function could be top-heavy, compared with the present day if conditions favour the formation of more massive stars. A top-heavy distribution would increase ultraviolet output per unit mass formed, which would in turn affect the conversion from luminosity to star formation rate. Observationally, constraints on the initial mass function at these times remain indirect. Analysts therefore present a range of star formation rates based on standard assumptions, and note that uncertainties are wide. Even with these caveats, GN-Z11 appears to sustain star formation at a pace that is large when scaled by its small mass, which is consistent with theoretical expectations for young halos fed by cold gas streams in a dense cosmic environment. Redshift also sets the conversion between an observed line's wavelength and its rest frame identity. When spectra are deep enough lines from ionized oxygen, ionized carbon or hydrogen can be identified in the infrared at positions predicted by the measured redshift. Their strengths relative to the continuum provide independent checks on star formation rates and on the hardness of the radiation field, which in turn relates to stellar population ages and metallicity. In the highest redshift regime, many common lines are shifted beyond practical observing windows, or are attenuated by the intergalactic medium, so detections are rare and low signal to noise. When present, even a single secure line can anchor the redshift and reduce the uncertainty that photometric estimates carry. When absent a strong break and consistent colours across multiple instruments, can still constrain redshift well enough to place the source within the early epoch reliably, gravitational lensing can modulate the observed flux without changing colours. A weak magnification by foreground large-scale structure can brighten a source by a modest factor. Strong lensing near massive clusters can create arcs and multiple images with higher magnifications. For GN-Z11 fields are checked for known lenses and for patterns of distortion in nearby galaxies that would signal strong lensing. In most analyses, the lack of strong lensing features and the compact, nearly symmetric appearance support the view that any magnification is small. A small magnification would not change the qualitative placement in time, but would slightly adjust inferred intrinsic brightness and star formation rate downward. This possibility is accounted for as an uncertainty rather than a change in classification. Cosmic variance affects counts and environments at this edge. A single bright source can reside in a region that will later host a small group or a large halo, while neighbouring fields could be sparse. Because deep surveys cover limited areas, the distribution of early galaxies derived from them carries large sample variance. GN-Z11's field is therefore compared with others at similar depth to see whether the number of candidates at comparable redshift is unusually high or low. The answer helps judge whether the source sits in an overdense region that might hasten its growth through mergers or in an average field where isolated growth dominates. At this stage, the conclusion is modest. One bright compact object flagged by a strong break set within a sparse map where environment is still forming. All these steps tie back to the timeline conversation with care about units and definitions. Ages are read as look-back times in billions of years. Sizes are physical at emission expressed in light years or in parsecs written in words. Luminosities translate from fluxes using luminosity distance appropriate to the measured redshift. Star formation rates are stated with their dependence on assumptions about the initial mass function. Dust content is inferred from continuum slope with caveats about metallicity. Each statement remains within what the light can support without invoking models beyond the minimal ones needed to turn observed numbers into physical quantities. The aim is to keep the path clear. Light stretches dimming is strong selection, uses a break in spectra or strong colour criteria, fix redshift to an early time. Within this lightest time frame, GN-Z11 stands as a compact source, whose photons left when the universe was young travelled across a medium that was still clearing and arrived redshifted into the infrared where space telescopes can see them. The measured break, the blue continuum, the small angular size and the absence of strong lensing features together outline a young low-dust star-forming galaxy of small physical extent, high specific star formation rate and placement near the boundary between neutral and ionized intergalactic gas. The next step moves inward again, without changing tone, turning from the photon journey to the instruments that first separated this signal from the background, the imaging that set the colour criteria and the spectroscopy that put sharper bounds on the redshift and the properties of the source. The detection of GN-Z11 begins with imaging that sorts faint sources by colour and shape, and proceeds to spectroscopy that tests whether the colour break arises from neutral hydrogen at extreme redshift or from dust and old stars at intermediate distances. The Hubble Space Telescope lays the groundwork with deep near-infrared imaging from the Wide Field Camera 3 using filters whose band passes straddle the wavelength, where the hydrogen break would fall if the source lay in the first few 100 million years. The candidate appears as a non-detection in bluer filters and as a compact, slightly resolved source in redder ones with flux that repeats across visits and dithers. Point spread function matched photometry measures its brightness consistently in each band, and size measurements after deconvolution with the instrument's point spread function show a half-light radius that is small but larger than a perfect point indicating that the object is not a foreground star. Template fitting of the spectral energy distribution returns a photometric redshift probability distribution that peaks at extreme redshift and leaves only a small tail at lower redshift, which would require fine-tuned dust reddening and an unusually strong spectral break in a galaxy that otherwise lacks matching features. This imaging step does not determine redshift uniquely, but it reduces the space of possibilities to a compact high redshift solution that is stable under changes in aperture background box size and photometric method. Grism spectroscopy with Hubble's slitless spectrographs follows as a first attempt to separate light by wavelength, without pre-selecting a slit. In this mode, every source in the field is dispersed, and spectra overlap unless careful roll-angle planning and contamination modelling isolate the target. For GN-Z11, the dispersed trace shows a continuum that rises only redward of the expected hydrogen break and remains at the background level blueward, consistent with a strong discontinuity at the position implied by the photometric redshift. The Grism's resolution is low, so individual narrow lines are not cleanly resolved, and the damping wing shape on the red side of the break is hard to measure. Even so, the mere presence of a continuum only at redder wavelengths and its absence at bluer ones supports the extreme redshift interpretation, and disfavours dusty, lower redshift solutions that would tend to leave residual flux shortward of the break. Careful simulations of contamination from neighbouring traces and persistence artefacts reduce the risk that a nearby source is masquerading as the break. The result is a preliminary spectroscopic anchor, a continuum edge, at the expected position. The James Webb Space Telescope extends this work by adding sensitivity and spectral resolution in the infrared where the most informative features of early galaxies land after redshift. Imaging with the near-infrared camera confirms morphology and colours with filters narrower and deeper than those available to Hubble, tightening the photometric redshift and refining the half-light radius with a cleaner point spread function. The source remains compact and slightly extended with no diffraction spikes or anomalous shapes that would signal a star or an artifact. The improved depth places stronger limits on flux blue ward of the break, further suppressing lower redshift solutions. Spectroscopy with the near-infrared spectrograph then seeks a decisive measurement. Multi-object spectroscopy allows a slit to be placed on the candidate, separating its light from neighbours, and avoiding the overlap that complicates slitless modes. Low to medium spectral resolution is chosen to balance sensitivity with the ability to trace the continuum edge and to search for faint emission lines. In the highest redshift regime, resonant hydrogen emission can be attenuated by neutral gas in the surrounding intergalactic medium and within the galaxy itself, so the absence of a bright line does not argue against the early epoch interpretation. Instead, the most robust signature becomes the continuum break itself, and any gentle slope redward that carries the imprint of stellar populations and dust. For GN-Z11 spectra show an abrupt drop that aligns with a hydrogen break at the photometric redshift and a smooth continuum at longer wavelengths. When lines appear, they are weak and often consistent with nebular emission from oxygen or carbon at positions that match the break-based redshift, but their low signal-to-noise and the possibility of interlopers from skylines demand caution. Analysts therefore prioritise the continuum edge as the redshift anchor and treat line identifications as supporting rather than primary evidence. The key point is that the break position in the near-spec spectrum agrees with the break implied by NIRCam colours and Hubble photometry, and that the continuum shape is consistent across instruments. Instrument systematics are addressed directly because the placement near the observational limit requires that small biases do not masquerade as strong claims. Flat field residuals and detector persistence can create artificial dips or rises if not modelled. Deep calibrations and dithering strategies mitigate these by moving the source across pixels and averaging over small-scale sensitivity variations. Wavelength solutions are checked against skylines and internal calibration lamps to ensure that the break is not misregistered. Flux calibration is tested by observing standard stars and by comparing overlapping filters in imaging and spectroscopy. In JWST, data thermal stability and mirror alignment reduce time-dependent drifts that could blur faint features. For Hubble Grism, data multiple roll angles and contamination models guard against overlap, When all of these guards are applied, the break in GN-Z11 remains where high redshift demands and the red continuum persists, which strengthens the detection. Source classification tests extend beyond instrumental concerns to astrophysical contaminants. Cool dwarf stars in the Milky Way can present red colours, but their spectra carry molecular absorption bands that differ from a sharp hydrogen break, and their point-like shapes at space-based resolution distinguish them from slightly extended distant galaxies. Dust-reddened galaxies at intermediate redshift can mimic red colours, but their continua blue ward of any dust feature usually remain above zero in deep data, and their mid-infrared fluxes relative to near-infrared fluxes follow patterns unlike those of a young low metallicity galaxy. GN-Z11 fails to match cool star templates in spectral shape and size and does not resemble dusty interlopers once the non-detection's bluewood of the break are stacked to lower noise. Weak lensing magnification can boost flux, but does not alter the position of the break. The lack of strong lensing features and the regular shapes of nearby galaxies suggest only mild magnification at most, which is folded into uncertainties on intrinsic luminosity rather than into redshift determination. The redshift determination from the continuum edge unlocks physical estimates that depend on distance. Absolute magnitude in the rest frame ultraviolet can be computed from the observed flux, and the luminosity distance appropriate to the measured redshift. This magnitude, combined with standard conversions that relate ultraviolet luminosity to current star formation under an assumed initial mass function, yields a star formation rate with explicit caveats that the conversion could differ in the early universe if stellar populations are skewed toward higher masses. The slope of the ultraviolet continuum constrains dust with very blue slopes, implying little attenuation and aligning with low metallicity expectations. The half-light radius measured from near-cam imaging translates to a physical size of only a few hundred to a few thousand light-years at emission, which is small compared with present-day galaxies and in line with a nascent system. Together, these values place GN-Z11 among the brighter and more compact galaxies known at this epoch, not because it rivals modern spirals in mass, but because its star formation activity is high for its size and age. Spectroscopy also probes the interstellar medium indirectly. The presence or absence of nebular lines and their ratios when measurable provide hints about gas temperature ionization parameter and metallicity. In cases where oxygen lines are detected at extreme redshift, high ratios can indicate hard radiation fields from young massive stars and low metal content. If helium lines appear, they speak to very hot massive stars or to low metallicity environments. For GN-Z, 11-line detections are at the threshold where identification must be cautious. Thus, the most secure inferences rest on the continuum slope and break. Even so, the lack of strong dust reddening and the compact size sit comfortably with a picture of low metal content, vigorous star formation, and a radiation field capable of contributing to local ionization during the reionization epoch. A practical advantage of JWST's spectroscopic modes is the capacity to search for faint continuum in windows between bright skylines and to integrate long enough to average over detector noise. For extreme redshift galaxies, the break sits in regions where terrestrial telluric absorption would prevent ground-based conformation. JWST avoids this by operating above the atmosphere. The stability of the space environment also improves sky subtraction, which is critical when the signal resides only slightly above the background. In this context, GN-Z11's spectrum from JWST serves to lock down the redshift and to refine the photometric picture rather than to unveil a rich forest of lines. The value lies in the agreement among independent instruments and methods. Hubble imaging selects the candidate. Hubble GRISM data show a continuum only redwood of the break. JWST imaging confirms colour and size. JWST spectroscopy places the edge at the expected wavelength and records a consistent red continuum. All steps include explicit uncertainties. The exact redshift carries a small error determined by how sharply the continuum break is measured and by the spectral resolution. The intrinsic luminosity carries an error from possible weak lensing magnification, and from flux calibration. The size carries an error from deconvolution with a finite point spread function, and from the assumed light profile. The star formation rate carries the largest error because it depends on the initial mass function and on the fraction of ionizing photons that escape or are absorbed and reprocessed. These uncertainties are quoted when numbers are given in later sections. The detection claim itself does not rest on small error bars. It rests on the robustness of the break across instruments and on the consistency of morphology and colours with a compact galaxy at extreme redshift. With telescopic detection now anchored, the path can move one step inward to the physical setting implied by such an early appearance. The next section keeps the same measured tone and turns from instruments and redshift to the environment of the young universe. At this epoch, a denser, warmer cosmic medium threaded by growing dark matter halos, short cooling times for primordial gas, and the first sustained episodes of star formation that build compact galaxies whose light stretched by expansion reaches present telescopes as the faint red continuum that flagged GN-Z11 in the first place. The cosmic environment that receives the light, now labelled GN-Z11, is young, dense and simple in composition. Baryons are mostly hydrogen and helium, left from the first few minutes with trace amounts of heavier elements, too small to change gas cooling except where the first stars have already lived and died. The mean density of matter is higher by large factors compared with the present day, so gravity gathers material quickly into the earliest dark matter halos. These halos form first at small masses, and then merge into larger hosts, laying down a hierarchy that sets where gas can collect. In this epoch, the characteristic halos that host the brightest visible galaxies have masses far below those of modern large spirals, yet are deep enough that gas falling in can be heated to thousands, to tens of thousands of degrees, Kelvin cool by atomic processes and settle toward the centre. The intergalactic medium around them is not yet fully ionized. Neutral hydrogen pervades wide regions, raising the opacity to ultraviolet photons and making the hydrogen break a strong selector in imaging. The galaxy and its surroundings thus sit at the boundary between a diffuse partly neutral outside and the first ionized bubbles that young stars carve around their hosts. Inside a halo of the appropriate mass gas accretion proceeds along filaments of the early Webb. Streams deliver cold material to the central regions, without always shocking to high temperatures, a process that is favoured when halos are small and the cooling time is short compared with the dynamical time. Where shocks do form, they heat gas to the virial temperature set by the halo mass, after which the gas radiates away energy through atomic line emission and sinks inward. The absence of metals limits cooling channels, but atomic hydrogen and helium lines remain efficient at the densities present, so the bottleneck is not the physics of cooling as much as the supply of gas and the pressure from feedback once stars ignite. At these redshifts, the cosmic microwave background temperature is higher than today by a factor equal to 1 plus the redshift adding a mild floor to the temperature of dust and setting a background against which faint, far infrared emission must rise. Within the galaxy, this background does not prevent star formation. It only changes the contrast in certain bands and slightly alters the balance of heating and cooling for the coldest phases that may exist in compact pockets. The first episodes of star formation are seeded in dense clouds that form as gas loses pressure support and fragments. The initial mass function, which describes how many stars form at each mass, may favour higher masses when metallicity is near zero because cooling is less effective at allowing gas to break into many small pieces. Even a modest shift toward massive stars raises the output of ionizing photons per unit. Mass formed hardens the radiation field and shortens stellar lifetimes. In such conditions, young stellar populations produce strong ultraviolet continua, and when permitted by the surrounding medium bright nebula lines. They also launch stellar winds and after short lifetime supernovae that inject momentum and energy into the interstellar medium. The feedback regulates the next round of star formation by stirring gas-raising turbulence and opening channels through which hot gas can escape into the halo. In a small system, the depth of the potential well is limited, so feedback can drive outflows that carry away a fraction of the gas, reduce the immediate fuel supply, and enrich the surroundings with the first heavy elements. The interstellar medium thus becomes multi-phase. Pockets of dense cold gas collapse into stars. Warm ionized gas fills the regions around young clusters. Hot bubbles from supernovae and winds break out and vent into the halo. The mix evolves on timescales of millions to tens of millions of years, which is short compared with the look-back time, but long enough that the light observed at a single epoch records an average over several stellar generations in such a small system. The galaxy's small size follows from the limited mass and the short assembly time. Half-light radii of a few hundred to a few thousand light-years are natural when the stellar component is concentrated in the inner parts of a young halo, and when the outer regions are still dominated by gas that has not yet cooled completely. The observed compact morphology at infrared wavelengths aligns with this expectation. Within that radius, the surface density of star formation can be high, despite the total mass being modest, and the ultraviolet continuum can be bright for the size. This combination pushes the source above survey limits even as surface brightness dimming is severe. The immediate environment beyond the visible extent is a halo of gas that shares the dark matter potential. Its temperature density and ionization state set how easily outflows escape, and how well ionizing photons from young stars travel into the intergalactic medium. If the halo gas is clumpy, photons thread low-density corridors and begin to ionize a bubble that grows with time and with star formation rate. If the gas is smooth and dense, many photons are absorbed near the source and reprocessed, weakening escaped hydrogen emission and deepening the continuum break. In either case, the early galaxies contribute to reionization by adding ionizing photons to their neighborhoods. The role of any single object depends on its star formation rate, the fraction of ionizing photons that escape, and the duty cycle of bursts. GN-Z11 sits where even a single compact system forming stars rapidly for its mass can have a measurable local effect. Mergers are frequent in this era and contribute to growth. Small halos merge into larger ones, sometimes triggering bursts of star formation as gas compresses. The times between mergers are short enough that a compact galaxy can experience several minor interactions over a few 100 million years. Each event adds mass and can thicken the stellar distribution or induce clumps that later migrate inward. The observed compactness does not preclude such activity. It implies that even with mergers, the system has not yet grown a large extended disk and remains centrally concentrated. Over longer times, continued merging would build a larger descendant, but within the current layer, the focus remains on the present assembly state, a small halo, a compact stellar component, and an active interstellar medium where feedback and inflow balance. The chemical state of the gas reflects the few cycles completed so far. Heavy elements are present at low levels once the first supernovae explode and dust begins to form in their ejecta and in dense clouds, but the overall metallicity remains low. This keeps ultraviolet continua relatively blue and reduces attenuation matching the observed color slopes. It also changes the cooling curve only modestly in the temperature range where atomic lines already dominate, so the star formation regulation is set more by feedback than by a lack of cooling channels. Nebular line ratios, when detectable, point to hard radiation fields and high ionization parameters consistent with young low metallicity stars. The surrounding intergalactic medium remains the largest influence outside the halo. Patches of neutral hydrogen impose a high optical depth blue ward of the hydrogen break, which makes the selection of such galaxies possible and sets the contrast that defines their detection. The same medium alters the appearance of resonant lines and sets the damping wing on the red side of the break. As ionized bubbles overlap with time, the neutral fraction drops and escape of resonant photons increases. GN-Z11's placement within this process is read from the spectrum shape and any faint line detections. Either an early ionized bubble or a more neutral local environment is consistent with the patchy progression of reionization at these times. Dynamics inside the halo proceed calmly by cosmic standards. The rotation curve, if it exists in a settled sense, is truncated at small radii. Velocity dispersions in the young stellar component and gas are high compared with present-day thin disks because turbulence from feedback and irregular inflow stirs the medium. This turbulence helps support the gas against collapse between bursts and spreads energy from supernovae across the interstellar medium. It also thickens any nascent disk and maintains clumps that form stars efficiently before shear and pressure tear them apart or cause them to sink toward the center. The timescales for these processes are millions of years short compared with the interval that the redshift stretches, by meaning that many such cycles can occur within the span that the observed continuum averages over. The connection to the cosmic web remains direct. Thin filaments feed the halo with fresh, mostly pristine gas, while also delivering small satellites. This supply maintains high gas fractions even as star formation consumes material and outflows vent some fraction into the circumgalactic medium. The balance between inflow-outflow and star formation sets the specific star formation rate and keeps the galaxy luminous in the rest frame ultraviolet despite its small mass. When inflow slows or feedback strengthens, star formation dips. When inflow rises or outflows weaken, it climbs. The observed light catches the system in one of these states, but the mean over tens of millions of years is the quantity that the continuum most directly traces. Within this environment, GN-Z11's appearance as a compact blue high redshift source is a natural outcome. A small early halo draws in gas efficiently. Short cooling times permit rapid star formation. Low metallicity keeps colors blue. Feedback regulates without quenching. And the surrounding neutral medium strengthens the hydrogen break while moderating resonant line escape. The result is a faint resolved galaxy, whose light has crossed most of cosmic history, to arrive red-shifted into the infrared where space telescopes can record its continuum and place it within the timeline of galaxy formation at the edge of current reach. The next inward step, keeping the same steady tone, turns to the stellar content itself, the likely mix of massive short-lived stars that dominate the ultraviolet, the first chemical enrichment from their deaths, and the feedback they drive into the small interstellar medium that shapes the subsequent pace of growth. The light that reaches present instruments from GN-Z11 is dominated by massive short-lived stars that pour out ultraviolet radiation while they live and seed the first enrichment when they die. In a low metallicity environment, gas cools less efficiently into many small fragments, so the distribution of stellar masses can tilt toward higher masses compared with the present day. Even a mild tilt amplifies the ionizing output. Per unit mass formed, hardens the spectrum and shortens the typical lifetimes to a few million years. Within compact clouds, gravity gathers gas until radiation pressure stellar winds, and heating from young stars slow further collapse. The result is a rhythm of clustered formation, in knots a few tens to a few hundreds of light-years across each carving an ionized bubble in the surrounding medium. These bubbles overlap within the galaxy and leak through low-density channels toward the halo. The fraction of ionizing photons that escape into the intergalactic medium depends on the porosity of the interstellar gas, on the geometry of feedback-carved cavities, and on the balance between ongoing inflow and recent supernova clearing. In a small system, the same energy that ionizes gas also pushes on it. Outflows lift material out of the densest regions and carry metals into the halo. This coupling regulates star formation by reducing the immediate fuel supply and by stirring what remains into a multi-phase mixture, where only the densest pockets can cool quickly enough to form the next generation of stars. Chemical enrichment begins almost immediately on cosmic timescales. The first supernovae inject heavy elements into the gas-raising metallicity from near zero to low values that nonetheless start to alter cooling and dust formation. Dust condenses in supernova ejecta and in dense clouds, but at this stage the total dust mass remains small. A low dust content keeps the ultraviolet continuum blue, which is consistent with the slopes measured in infrared bands after redshift. Where dust exists, it absorbs ultraviolet photons and re-radiates in the far infrared. At the redshift of GN-Z11, the background temperature of the cosmic microwave radiation is high enough to warm dust slightly, reducing contrast at long wavelengths so faint dust emission can be difficult to detect even if present. The net effect is that blue continua are expected with only mild attenuation and little sign of a strong discontinuity from an older, redder stellar population. A weak or absent signature of an age break in the continuum also follows from the youth of the system. The stars that dominate the light are short-lived, and intermediate mass stars whose photospheres would imprint a stronger break have not yet had time to evolve in large numbers. Spectral features, when measurable, carry fingerprints of these populations. Nebular lines from ionized oxygen, carbon and hydrogen trace gas excited by hard radiation fields. High-line ratios point to hot massive stars and low metallicity, where cooling lines are fewer and gas temperatures in ionized regions are higher. If helium lines appear, they require especially hard spectra, and add weight to the case for very massive stars. In the highest redshift regime, resonant hydrogen emission can be suppressed by neutral gas in the galaxy and in the intergalactic medium, so the absence of a bright line is compatible with vigorous star formation if the local neutral fraction is high. Continuum slopes remain the more robust measure at these depths, and in GN-Z11 they align with low dust and young populations, where lines are weakly detected at wavelengths. Predicted by the continuum break, they serve as checks on metallicity and on ionization parameter rather than as the primary redshift anchor. The internal energy budget is shared among radiation winds and supernovae. Radiation pressure acts first, pushing on dust and gas in the immediate vicinity of clusters. Stellar winds add momentum over the few million years before the most massive stars end their lives. Supernovae then deposit sudden energy and momentum into the surrounding medium driving shocks that heat gas and compress neighbouring clouds. In a compact galaxy with high gas fraction, these shocks can both destroy and create star-forming sites. They clear channels that vent pressure out of the system, and they compress filaments that may later collapse. The efficiency with which injected energy becomes large-scale outflow depends on the depth of the potential well, and on how quickly cooling removes thermal energy from shocked gas. In low metallicity, gas cooling is less efficient at certain temperatures, which can keep hot bubbles overpressured longer and increase the chance that they break out of the disk, such as it is into the halo. Once in the halo, hot gas expands and mixes, and part of its energy converts into turbulence that supports the circumgalactic medium against collapse. This same turbulence helps distribute the first metals beyond the visible galaxy, seeding later inflows with trace elements that will alter cooling in subsequent cycles. Star formation in such a regime is clumpy rather than uniform. The high surface densities reached in a compact half-light radius drive high specific star formation rates even when the total mass remains modest. Clumps can migrate inward under dynamical friction and through interactions, feeding a central concentration of stars and gas that may later form a bulge-like component. Their lifetimes are short in the face of feedback and shear, yet new clumps appear as inflow continues along filaments of the cosmic web. This constant renewal sustains the ultraviolet continuum at a roughly steady level on the long timescales imposed by redshift, even though the instantaneous rate in the galaxy frame may fluctuate. The observed light is thus a time-averaged sum over many clustered events, each a few million years long, spread across the compact body of the galaxy. Binary stars and compact remnants add a high-energy tail to the spectrum that is not always visible directly at these depths, but influences the gas. High-mass X-ray binaries form rapidly after the first supernovae, and their hard photons can preheat or partially ionize diffuse gas, changing the escape routes for ultraviolet light and the cooling path for the halo. Cosmic rays accelerated in supernova shocks contribute pressure and can leak from the disk into the halo, adding another gentle support that helps drive outflows. These channels are secondary in the energy budget compared with radiation and thermalized supernova energy, but become consequential in small systems where every pressure source alters the fragile balance between inflow and feedback. The initial stellar mass distribution shapes how much light each mass range contributes. Very massive stars dominate the ultraviolet but die quickly. Intermediate mass stars add to the blue and near ultraviolet continuum for tens to hundreds of millions of years and will eventually become sites of dust formation in slow winds. But at the epoch of GN-Z11, their contribution is still growing. Low-mass stars live far longer and contribute little to the observed ultraviolet continuum. They store mass that will shine mainly at redder wavelengths at later times. Because observers see the system near its first sustained episodes, the light is biased toward the short-lived tip of the distribution, and inferences about the total stellar mass must be made with care. Conversions from ultraviolet luminosity to stellar mass depend on assumed star formation histories, and on the faint contribution of older stars, which is hard to measure directly when the continuum is dominated by the young. Analysts therefore carry a range of mass-to-light ratios consistent with blue slopes, and with the absence of a strong age break leaving stellar mass estimates as bands rather than single values. Feedback does not simply quench, it sets a cadence. After a burst, energy and momentum disperse gas-lowering densities and temporarily reducing star formation. Inflows then refill the inner regions and cooling re-establishes dense clouds. The time between bursts reflects how quickly gas can return and how strongly the last episode cleared paths. In a compact galaxy, this cadence can be short, so the ultraviolet output appears steady in the observer frame, even if it pulses in the galaxy frame. The coupling between this cadence and the escape of ionizing photons determines how much GN-Z11 contributes to local reionization. If bursts open low-density channels that remain for some time, the escape fraction rises, and the galaxy carves a larger ionized bubble. If dense gas refills channels quickly, the escape fraction falls, and more ionizing photons are trapped and reprocessed. Either state can prevail at different times. The spectrum records which holds during the observing window as a balance between faint line emission continuum slope and the depth of the hydrogen break. The earliest chemical cycles also leave spatial patterns. Metals concentrate near young clusters and in outflow cones, and remain lower in neutral gas that has not mixed recently. Overlap of ionized bubbles around multiple clusters evens these gradients, while inflow of pristine gas reinstates sharpness. The resulting patchwork controls when new stars form and how their radiation interacts with the medium. In a small galaxy, the scale of this structure is comparable to the half-light radius, so observations at current resolution see an integrated field rather than distinct zones. The blurred average still contains clues. A blue global slope compact size and lack of a strong age break argue that metal and dust enrichment has begun but not yet transformed the spectrum into one dominated by older stars and heavy attenuation. None of these elements require exotic physics. They are the familiar processes of star formation, and feedback run in a regime where metallicity is low. Gas fractions are high, sizes are small, and timescales are short. What changes at extreme redshift is the frequency and the relative weight of each channel. Massive stars are more influential because they are relatively more common. Supernovae and winds have wider reach because potentials are shallower. Escape of ionizing photons is more decisive because the surrounding medium is more neutral, and inflow is more persistent because the Webb is denser and closer. GN-Z11 fits this pattern as a compact blue star-forming galaxy whose light is the composite of many clustered events, and whose surroundings are being altered by the first rounds of feedback and enrichment. In this layer, the focus remains on the stars that drive the observed light and the immediate gas they shape. The next inward step, keeping the same slow register, turns to how these young populations and their feedback leave signatures in the spectrum that allow estimates of star formation rate metallicity and dust to be drawn with explicit caveats, and how those estimates place GN-Z11 within the broader distribution of early galaxies at similar epochs in surveys that reach the same depth, translating GN-Z11's faint infrared light into physical quantities begins with a continuum because at this redshift the continuum is the most secure measurement. The rest frame ultraviolet slope measured across adjacent filters, redwood of the hydrogen break, sets the first constraint. A very blue slope implies little dust and a hard radiation field from young massive stars. Analysts fit this slope with simple stellar population models that assume continuous star formation over tens of millions of years, low metallicity, and an initial mass function that may tilt slightly toward high masses. The best-fitting models reproduce the observed colours without invoking heavy dust attenuation, which would redden the slope and reduce ultraviolet output. With dust corrections held small, the ultraviolet luminosity converts to a star formation rate using calibrations that relate photon production to the mass of stars formed each year. These calibrations carry a factor that depends on the initial mass function. A distribution richer in massive stars produces more ultraviolet light per unit mass, and thus lowers the inferred rate for a given luminosity. Because the early universe may favour such a distribution, results are expressed as ranges that reflect this uncertainty. Even with this caveat, GN-Z11's luminosity points to a rate of forming stars that is high for a system of such small size, yielding a specific rate that exceeds the typical values in present-day galaxies by large factors. A second continuum features the absence of a strong age break between the far ultraviolet and the near ultraviolet at these wavelengths indicates that intermediate age stars have not yet accumulated in numbers large enough to imprint their photospheric signature. If any Balmer break from older stars exists, it is weak at the depths reached so far, which favours a young luminosity-weighted age, and supports the picture of ongoing recent star formation, rather than a long quiescent build-up. Nebula continuum, the smooth light from gas that is ionized by the same stars, can fill in a weak break, so fits include this component as well. The combined constraint keeps the allowed star formation histories young, and rising with little room for a dominant older population that would otherwise shift colours to the red. Spectral lines, when present, refine these inferences. At extreme redshift, the strongest line from hydrogen can be diminished by neutral gas in the galaxy and the surrounding medium. In that case, weaker lines from oxygen or carbon, if detected at the wavelengths predicted by the continuum break, provide the checks. Ratios of oxygen lines to the continuum reflect the hardness of the radiation field and the ionization parameter. High ratios are common in low metallicity, vigorously star-forming regions and match expectations for young hot stars. Carbon lines in the far ultraviolet when visible arise in gas, excited by hard spectra, and can indicate low metallicity and strong radiation pressure. In GN-Z11, such lines lie near the threshold of detection, so the safest course is to treat them as supportive hints rather than anchors. Their presence at the right wavelength strengthens the early epoch interpretation and points toward low metal content. Their absence at high significance would challenge that view, but current depths do not demand such a reversal. Dust estimation at this epoch relies on the ultraviolet slope because far infrared measurements of faint high redshift galaxies remain challenging. A blue slope typically translates into a small dust attenuation when standard relations built from lower redshift samples are applied. Those relations may evolve, but they offer a starting point. Applying them yields dust corrections that do not dominate the ultraviolet luminosity, so the star formation rate is not boosted dramatically by hidden light. Independent tests using line ratios would be stronger yet at these redshifts. Many of the usual pairs lie outside accessible windows or are absorbed. In their absence, the continuum slope remains the main dust gauge, and in GN-Z11 it indicates that dust plays a secondary role. This fits with the chemical youth expected when only the first few rounds of star formation have had time to produce and process heavy elements into grains. Stellar mass follows from fitting the full spectral energy distribution across all available bands. These fits combine the young, bright component that dominates the ultraviolet with any older, fainter component that could lurk underneath. Because the older light is hard to isolate at present depths, the mass-to-light ratio remains the largest single uncertainty. The allowed range includes models with steady star formation over tens of millions of years, and models with recent bursts on top of a small underlying mass. The half-light radius measured from high-resolution imaging sets the scale over which this mass is packed. The result is a compact stellar system with mass well below that of modern large spirals and size smaller by orders of magnitude, yet with a luminous output per unit mass that is high. This combination is the signature of a young galaxy caught during an intense phase of growth. With size and mass in hand, the surface density of star formation and the dynamical time can be estimated. The surface density rises because the same luminosity emerges from a small area, and the dynamical time shortens because the radius is small, and the characteristic velocities implied by potential depth remain modest. Short dynamical times and high surface densities favour clumpy, bursty star formation, as feedback and gravity compete on timescales of only a few million years. This regime naturally sustains high specific star formation rates and aligns with the blue continuum. It also promotes channels for ionizing photons to escape, because clustered feedback can open low-density paths through which radiation reaches the halo and beyond. The escape fraction remains an uncertain parameter. It depends on geometry that current images cannot resolve. Analysts therefore present a range of plausible values and consider the implications for local reionization. Even a moderate fraction, combined with the high specific star formation rate, yields enough escaping photons to ionize a bubble around the galaxy that grows with time. Placing GN-Z11 within the distribution of early galaxies uses luminosity functions derived from deep fields. The source sits at the bright end for its epoch not because its total mass is large, but because its star formation per unit mass is high and its dust attenuation is low. Bright end counts are sensitive to cosmic variance and to rare, rapidly growing systems. A single detection cannot set a global abundance, but it shows that such objects exist and gives a concrete example for models that predict the frequency of intense star formation in small halos at very early times. Its compact size falls along the steep size-redshift relation seen across samples where half-light radii decline rapidly toward early times. Its inferred mass and specific star formation rate align with the trend that less massive younger galaxies at high redshift form stars more rapidly relative to their mass than their later counterparts. The context of reionization adds a layer to this placement. The contribution of galaxies like GN-Z11 to reionization depends on three quantities that the data bracket, rather than fix the number of such galaxies per unit volume, their star formation rates, and their escape fractions. Surveys measure the first two statistically as samples grow. The third remains the most uncertain. The spectrum of GN-Z11 shows a deep break and a blue continuum. If a resonant hydrogen line is weak or absent, it may reflect a surrounding medium that is still partly neutral or a geometry that traps photons. Conversely, if a faint line is present, the local region may already be ionized. Either way, the object sits at the right time and brightness to contribute meaningfully to the ionization budget, and its detection demonstrates that compact efficient galaxies populate the early Webb. Comparisons with theoretical models are made cautiously. Simulations that include gas dynamics, star formation, and feedback predict that small halos at early times can sustain high specific star formation rates, low metallicity, and compact sizes. They also predict duty cycles in which bursts alternate with quieter periods. GN-Z11 fits comfortably within this picture as a system observed during or shortly after a strong episode. Models also suggest that such systems will merge frequently over the next few 100 million years, growing in mass and size and building more complex morphologies. The observed compactness and high ultraviolet output are then the natural starting conditions for later assembly. Instrumental refinements from the James Webb Space Telescope sharpen all of these measurements. Narrower filters measure the continuum slope more precisely. Deeper exposures place tighter upper limits on flux blue ward of the break, reducing the possibility of low redshift interlopers. Spectra recorded at higher signal-to-noise allow a more exact placement of the break, and better searches for weak lines in windows between backgrounds. With these in hand, error bars on star formation, rate, dust size and redshift shrink, although uncertainties tied to the initial mass function and to star formation history remain. The key result persists a compact galaxy of small physical size, low dust content, low metallicity, high specific star formation rate and placement, at an epoch when the intergalactic medium is still clearing. Every number quoted inherits a band of uncertainty that is stated openly. The star formation rate depends on the initial mass function and on dust. The mass depends on the hidden contribution of older stars. The size depends on the assumed light profile and on deconvolution. The escape fraction depends on geometry that current data do not resolve. Within these bands, GN-Z11's properties occupy the region of parameter space that marks the first efficient systems small bright in the ultraviolet blue in slope and capable of carving local ionized regions. This is the role assigned by the light itself, not by speculation. With quantitative estimates now grounded in the spectrum and continuum, the path can move inward again, while keeping the same steady register. Turning to the ways feedback from these young populations shapes the circumgalactic medium around the galaxy, how outflows recycle material, and how the exchange between inflow and outflow governs the next steps of growth in a halo that is still assembling within the early cosmic web. Feedback from young stars in GN-Z11 couples the compact interstellar medium to a larger diffuse circumgalactic medium that fills the halo. Radiation winds and supernovae inject energy and momentum into gas near the star-forming clumps, and drive flows that rise from the body of the galaxy into the surrounding volume. The circumgalactic medium at this epoch is denser than in the present day, and is supplied continuously by filaments that feed the halo. Outflows therefore push against a real counterpressure rather than expand into a vacuum. The result is a layered structure, a central region where gas is multi-phase, and turbulent an interface where cool clouds and hot bubbles exchange mass and energy, and an extended halo where enriched material mixes with inflowing low metallicity gas. Radiation pressure acts first on dust and gas near star clusters, pushing along the lowest density paths and carving channels that increase porosity. Stellar winds add momentum over a few million years, heating local gas and filling cavities with hot plasma. Supernovae then deposit energy impulsively pressurizing these cavities further and sending shocks into the surrounding medium. In a compact galaxy, the escape condition is met when the pressure in connected cavities exceeds the weight of overlying gas along a continuous path to the halo. When this happens, a vent opens and material flows out as a galactic wind. The mass carried depends on the mass loading factor, the ratio of gas driven out to stars formed. In small early systems, this factor can approach or exceed unity, because potentials are shallow and gas fractions high. A high mass loading factor spreads metals beyond the stellar body and seeds the circumgalactic medium with traces that later observations can detect as absorption features in background sight lines once bright beacons become available at lower redshift. At the interface, cool clouds experience ablation by hot flows and evaporation by thermal conduction along magnetic field lines. Shear instabilities stir the boundary and shred clouds into filaments that may recondense in the wake as the mixed gas cools. Magnetic fields thread the region and can reduce mixing across field lines, extending cloud lifetimes and guiding heat flow. The net exchange sets whether recycled gas returns promptly to the galaxy or remains suspended in the halo. At low metallicity, cooling is slower at some temperatures, which allows hot bubbles to remain overpressured longer and to drive flows farther. As metals rise, cooling accelerates, encouraging condensation in the halo and returning gas to the body on timescales of tens to hundreds of millions of years. GN-Z11 sits in the regime where enrichment has begun but has not yet made cooling extremely efficient everywhere. So both outcomes occur, some material escapes to large radii and some returns after brief excursions. Kinematics in the circumgalactic medium follow from this balance. Outflowing gas moves at hundreds of kilometers per second when launched, but slows as it sweeps up ambient material and expands. Inflow from filaments persists at comparable or lower speeds, guided by gravity and reduced by pressure at the halo boundary. Where the two meet, shocks and contact surfaces appear, and stir turbulence that fills a large fraction of the halo volume. This turbulence broadens lines in spectra and supports gas against collapse between inflow events. It also spreads metals in patchy patterns, leaving enriched cones along vent directions and lower metallicity zones elsewhere. Over time, partial mixing reduces contrasts without erasing the overall trend of higher metallicity near the galaxy and along outflow paths. Ionization structure responds to both radiation and shocks. Close to the star-forming clumps, gas is photoionized and kept at temperatures of a few times 10,000 degrees Celsius. Farther out, collisionally ionized gas at higher temperatures fills cavities and channels. The transition region hosts a complex mix where intermediate temperature ions are abundant. The escape fraction of ionizing photons depends on how often these channels connect to the halo and on how quickly dense gas refills them. During and shortly after strong episodes, escape can be enhanced. During quiet intervals, escape can be reduced as gas closes paths. In a compact system with bursty star formation, the time-averaged escape fraction emerges from many such cycles. Even a moderate average multiplied by a high specific star formation rate supports a local ionized bubble in the intergalactic medium that grows while the galaxy remains active. Geometry in GN-Z11 is simple in gross outline and complex in detail. The half-light radius is small, so outflows cross the stellar body in a short time. The direction of least resistance can shift as clumps form and die, so vents may precess around the minor axis rather than remain fixed. In projection, at current resolution, this produces a roughly round or slightly elongated appearance without clear bipolar lobes, yet the anisotropy matters for escape and enrichment. Metals and ionizing radiation are preferentially exported along channels that opened most recently. This anisotropy also explains why resonant hydrogen emission can be weak, even when star formation is strong. If most sightlines intersect neutral gas or turbulent dusty interfaces, the resonant photons scatter and are absorbed before leaving the system, while non-resonant continuum escapes through small windows and arrives with a blue slope. Recycling closes the loop between the halo and the galaxy. Gas that cools in the circumgalactic medium can rain back toward the centre as clumps or filaments. The timescale for this return depends on radius, metallicity and turbulence. At small radii, return can occur within tens of millions of years and feed subsequent star formation with enriched material. At larger radii, return stretches to hundreds of millions of years and may be interrupted by mergers that deliver fresh gas on intersecting trajectories. The presence of even a small recycled component raises metallicity in the next generation of stars and increases dust formation, which then affects attenuation and radiation pressure, coupling in the following cycle. In this way, feedback and recycling regulate not only the rate, but also the spectral character of star formation as the system evolves. The circumgalactic medium also sets the efficiency of future accretion. If outflows heat a large fraction of the halo volume, inflowing filaments can be disrupted or diluted before reaching the core, lowering inflow rates temporarily. If outflows escape in narrow channels and leave most of the volume cool, filaments can continue to feed the centre with little hindrance. GN-Z11's compact size and high specific star formation rate suggest that outflows are present, but that they do not fill the halo uniformly. This is consistent with continued star formation at high surface density and with the blue continuum that implies modest dust buildup and sustained inflow. Over time, as metallicity rises and dust grows, Coupling between radiation and gas strengthens and outflows may widen, but within the current layer, the halo remains a partially filled reservoir rather than a fully heated bath. Observables that probe the circumgalactic medium at this epoch are indirect but informative. The depth and shape of the hydrogen break reflect both the galaxy's spectrum and the neutral fraction in its surroundings. A deep break with weak resonant lines points to a more neutral local medium or to blocked sight lines. The ultraviolet continuum slope already blue suggests low internal dust, so external absorption becomes the more likely cause of any suppression of lines. Faint metal lines, if detected, place lower limits on enrichment in outflowing gas and on ionization parameters in the interface regions. Sizes and morphologies place limits on the opening angles needed for escape. Each of these taken together outline a circumgalactic medium that is already enriched at low levels, turbulent from feedback, and threaded by channels of varying density that route both radiation and mass. Mergers modulate this environment without erasing its basic structure. Minor mergers add satellites whose gas joins the circumgalactic medium before sinking, stirring turbulence, and changing angular momentum in the core. Close passages can trigger new star formation by compressing gas-raising outflow power for short intervals. These events also bring in stars and metals, raising baseline metallicity. The cumulative effect over hundreds of millions of years is growth in mass and size, but in the current phase the signature remains a compact body with bursts controlling vent opening. Mass budgets incorporate these flows. The inflow rate from the Webb sets the upper bound on gas supply. The star formation rate removes a fraction to build stars. Outflows remove another fraction to the halo and beyond. Recycling returns part of that fraction on a delay. In steady state, over tens of millions of years, the sum of star formation and net outflow approximates the inflow. When outflows temporarily exceed the difference between inflow and star formation, the gas reservoir shrinks and star formation dips. When inflow rises after a merger or as filaments brighten, the reservoir grows and star formation climbs. GN-Z. 11's observed luminosity and small size imply it is in a phase where inflow plus recycling are supporting a high specific star formation rate, despite ongoing outflows, which is the regime needed to sustain the blue continuum at the measured level. The role of cosmic background radiation is small but present. The higher background temperature at this redshift sets a baseline for dust heating and can reduce the contrast of far infrared emission from the circumgalactic medium. It also shortens cooling times slightly for some transitions by providing a radiation field that affects level populations, but these changes are second order compared with the dominant processes of shock heating, photoionization, and adiabatic expansion. The main control remains mechanical and radiative feedback from the young population and the continuing supply from filaments. Time dilation seen by the observer compresses many cycles into a near-steady view. Vents open and close, clumps form and disperse, and clouds rise and fall on times of a few million years, while the observed window spans longer intervals. The measured continuum therefore averages over many episodes, smoothing stochasticity in escape and outflow rates. This smoothing aids interpretation of global quantities like specific star formation rate and mean dust attenuation, but hides the instantaneous structure of the circumgalactic medium. Future measurements with higher signal-to-noise and angular resolution may isolate small gradients in colour across the body that reflect recent local clearing, yet at present the integrated field remains the principal constraint. Within this feedback-governed exchange, GN-Z11's circumgalactic medium functions as both a buffer and a ledger. It buffers the galaxy by absorbing energy and momentum from young stars, spreading them over larger volumes, and returning a controlled fraction of mass on a delay. It records the first cycles of enrichment in patterns of metals and in the thermal structure of outflows and wakes. It sets the escape fraction by its porosity and determines how quickly local ionized regions grow. It responds to the cosmic web by admitting inflow along filaments and by mixing that inflow with recycled material. The consequence is a stable, high specific star formation rate, sustained in a compact system without catastrophic blowout or rapid quenching, a state that matches the blue continuum and small size read from the light. With the circumgalactic medium now placed around the compact interstellar body, and its exchange with the Webb and the wind described, the path can move one step inward again, without changing pace to the way these flows and young populations imprint detailed spectral signatures that allow constraints on metallicity ionization and kinematics to be drawn, and to how those constraints position GN-Z11 among other early systems observed at similar depths in fields that share the same methods. Spectral signatures at extreme redshift emerge as a narrow set of diagnostics that survive distance dimming and the filtering effect of a partly neutral intergalactic medium. The continuum redwood of the hydrogen break serves as the backbone. Its slope encodes dust and the temperature distribution of young stars. Its smoothness and lack of a strong age break limit the contribution of intermediate age populations. Superposed on this baseline faint emission and absorption, features provide leverage on metallicity ionization and kinematics when observed with sufficient sensitivity. Because line fluxes sit close to detection thresholds, the strategy favours integrated constraints that combine weak indicators rather than reliance on any single feature. Metallicity enters first through nebular emission ratios. In low metallicity, gas cooling lines are fewer, and the electron temperature remains higher in ionized regions, which boosts collisionally excited lines relative to recombination continua. Lines from doubly ionized oxygen and singly ionized oxygen, when measurable, respond strongly to temperature and ionization parameter. High ratios of oxygen lines to the ultraviolet continuum point to hard radiation fields from hot, massive stars and to low metal content. In the far ultraviolet intercombination lines of carbon and oxygen, trace gas at densities and ionization states, characteristic of compact energetic regions. Detections at the wavelengths predicted by the continuum break strengthen a picture of subsolar metallicity and intense star formation. In GN-Z, 11 such lines are faint, so analysis proceeds by comparing upper limits or marginal detections with stellar population models and photoionization grids that span plausible metallicities and ionization parameters. The allowed space favours metallicities well below solar values consistent with only a few cycles of enrichment having occurred. Ionization parameter. The ratio of ionizing photon density to gas density shapes both line strengths and the topology of ionized regions. High values arise when massive stars crowd into compact clumps, and when gas densities in those clumps are high. In this regime, lines from higher ionization states strengthen relative to those from lower states, and the continuum slope remains blue because dust is scarce. The same conditions boost the production rate of ionizing photons per unit star formation mass. GN-Z11's blue continuum compact size and high specific star formation rate place it naturally in the high ionization parameter regime. When line ratios are too uncertain to measure directly, the inference rests on consistency. The continuum requires hot young stars. Such stars in compact regions produce high ionization parameters, and the absence of strong dust signatures fits the same picture. Kinematics enter through line widths and through any resolved velocity offsets between features that trace different gas phases. At these redshifts, spectral resolution and signal to noise limit what can be extracted, yet even coarse measures carry meaning. Broadening beyond thermal widths points to turbulence and small-scale motions in ionized gas near star-forming clumps. Systematic offsets between faint nebular lines and the centroid of the continuum when measurable hint at outflowing gas that blue shifts resonant features, and at inflow that red shifts absorption lines imprinted by cooler material. In GN-Z11 such measurements are tentative, but they support a picture of modest turbulence and of flows consistent with the feedback cycle described earlier. Outflows from clusters that reach into the halo, and inflow from filaments that replenishes the core. Resonant hydrogen emission plays a special role because it is readily produced in H2 regions, but easily scattered by neutral hydrogen both inside the galaxy and in the intergalactic medium. At the epoch of GN-Z11, the neutral fraction around a given galaxy can still be substantial. The presence of a strong resonant line would imply a local ionized bubble or a line of sight with low intervening neutral gas. Its weakness or absence implies either internal trapping or a more neutral environment. The continuum break already signals a significant optical depth shortward of the threshold. Together with a blue slope, a weak line then argues that geometry and the external medium rather than dust dominate suppression. This reasoning leaves the escape fraction of ionizing photons as an open parameter that must be inferred indirectly. A blue slope and compact size favour moderate escape during burst phases. The weak line favours a patchy or neutral environment and significant scattering. A time-averaged moderate escape fraction reconciles these constraints. Absorption features offer a complementary view when signal-to-noise allows. Weak interstellar absorption lines in the far ultraviolet arising from metals in the cooler gas measure column densities and place lower bounds on metallicity. Their velocities relative to the stellar continuum trace bulk motions in neutral or low ionization gas. Stacked spectra of multiple objects at similar redshift often reveal such features statistically. For a single compact source like GN-Z11, limits prevail, though any detected line at the expected redshift with a small blue shift strengthens the case for outflows carrying enriched gas into the circumgalactic medium. Even non-detections are informative. Weak or absent absorption is consistent with both low metallicity and small path lengths through cold gas along the line of sight, which aligns with a clumpy, porous interstellar medium. Continuum fitting across a wider wavelength span refines stellar population parameters under explicit caveats. Models that assume continuous star formation over tens of millions of years, low metallicity and minimal dust most naturally reproduce the observed colours. Introducing a significant older component tends to redden the spectrum or to create a stronger age break than observed. Burst models superposed on a small underlying mass can also fit, provided the burst is recent enough that short-lived stars dominate the light. In all cases, the blue slope sets a hard limit on dust and on the fraction of light from older stars. Mass-to-light ratios inferred from these fits remain low compared with present-day galaxies, which is expected in a system where luminous short-lived stars dominate the flux. Positioning GN-Z11 among other early systems requires consistent selection and measurement across surveys. Deep imaging identifies candidates via the hydrogen break. Spectroscopy then confirms redshifts where possible and provides limited line diagnostics. When luminosities and sizes are measured uniformly, GN-Z11 lies at the bright compact end of the distribution for its epoch. Its inferred star formation rate per unit mass sits well above values common at later times, and its size falls along the steep trend of shrinking half-light radii toward early epochs. These placements are not isolated points. They align with ensembles of sources that taken together map the early luminosity function and the size-redshift relation. Cosmic variance and small samples widen uncertainties, yet the qualitative context holds compact blue-low metallicity systems with high specific star formation rates populate the first few 100 million years. Comparisons across instruments add robustness. Imaging from older facilities established the candidate list and initial sizes. New imaging refines colours and morphologies. Slitless spectra supplied the first continuum edges. Slit spectra place sharper breaks, and where possible detect faint lines. Consistency across these modes weighs against exotic interlopers and supports the early epoch classification. In particular, the agreement of break position between imaging colour cuts and spectroscopic edges anchors the redshift. The persistence of a blue slope across independent datasets anchors the low dust inference. The compact but resolved morphology anchors the galaxy classification rather than a point-like stellar contaminant. Together, these checks build a coherent set of properties. Uncertainties are folded into every derived quantity. Metallicity estimates from weak or absent lines become bounds rather than precise values. Ionization parameters inferred from continuum properties carry model dependence. Kinematics from barely resolved lines translate into qualitative statements about turbulence and flows. Yet the joint space these bounds define is small enough to be meaningful. GN-Z11 occupies the region of low metallicity, high ionization parameter, compact size, high specific star formation rate, and modest dust. Within this region, the exact values matter less than the pattern which matches theoretical expectations for nascent galaxies forming their first, substantial generations of stars. The reionization context adds a collective dimension. The contribution of a population of such galaxies to the ionizing photon budget depends on their number, density, their photon production efficiency, and their escape fractions. Surveys measure the first two with growing statistical power. The third remains inferred. GN-Z11 spectrum signals efficient photon production and leaves escape fraction open, but bounded by geometry and environment arguments. If many similar systems exist, even moderate escape fractions suffice to ionize large volumes by the time the universe has aged by a few 100 million years. If they are rarer or more dust-rich than current indicators suggest, larger escape fractions or contributions from faint undetected systems must compensate. In either case, GN-Z11 serves as a calibrator at the bright compact end anchoring the upper envelope of contribution per object. The connection to later evolution is implied but not yet measured directly. Compact low metallicity systems with high specific star formation rates are predicted to merge and to grow, building larger galaxies with more complex morphologies and richer chemical content. Feedback that now opens narrow channels will later broaden as dust and metals accumulate, altering the balance between radiation and gas. Disks may settle, bulges may assemble from migrating clumps, and the circumgalactic medium will carry a more pronounced memory in metal line absorbers at lower redshift. GN-Z11's current signatures thus mark an early stage on a path that many galaxies will follow, scaled by mass and environment. Instrument progress will sharpen these signatures. Higher signal-to-noise spectra will either confirm weak metal lines or push limits lower, tightening metallicity and ionization parameter bounds. Narrower filters will measure continuum slopes more precisely, reducing dust uncertainties. Improved spatial resolution will seek subtle color gradients across the compact body that betray recent clearing or dusty knots, translating integrated properties into spatially resolved ones. Each increment will reduce model degeneracies without altering the broad placement, a compact blue low metallicity galaxy in the first few 100 million years, forming stars vigorously for its mass and exporting radiation and metals into a dense evolving halo. In this layer, the spectral evidence limited yet coherent ties the light to physical conditions with cautious bounds. The next inward step proceeds with the same steady tone to the growth channel itself, how mass builds through inflow and merges on short cosmic timescales, how structure remains compact while assembly proceeds, and how the likely descendants of such a system appear at later epochs when the Webb has grown stronger, contrast and galaxies have accumulated longer memories in their stars and gas. Mass growth in GN-Z. 11 proceeds along two channels that operate together in the early Webb smooth inflow of gas, along filaments and discrete mergers with smaller halos that carry their own gas and stars. The smooth channel supplies a near-continuous stream of mostly pristine material that follows the gravitational potential into the halo and toward the compact core. Because the universe is denser at this epoch, by large factors the rate of supply per unit halo mass is high, and cooling times for infalling gas are short compared with the dynamical time. This promotes a steady rise in gas fraction within the inner region, and sustains star formation between bursts driven by mergers. The discrete channel adds steps on top of this smooth trend. Small halos themselves, hosts of young stars or gas-rich but faint systems, fall in along the same filaments and deliver packets of mass and angular momentum. Their passages compress gas-trigger new clumps and can tilt or thicken any nascent disk, keeping the morphology irregular and centrally concentrated. In a compact galaxy, the dynamical friction timescale for such small companions is short, so stars and gas from the satellites sink toward the centre and add to the inner mass rather than building extended outskirts immediately. This combination explains how structure can remain small in size. While mass rises, accretion feeds the core faster than it builds a wide envelope, and feedback keeps the outer gas stirred so that it does not settle quickly into a large thin disk. The rate at which halo mass grows can be expressed as a fraction per unit cosmic time that increases strongly toward early epochs. For halos of the scale that host bright compact galaxies at these redshifts, doubling times can be of order a few 100 million years. Star formation responds to this growth with its own cadence set by the balance of inflow, outflow, and turbulence. When inflow surges after a minor merger gas density in the inner kiloparsec rises, and the interstellar medium fragments into clumps that ignite star formation at high surface density. Feedback follows carving channels and driving winds that reduce density and temporarily slow the rate. Smooth inflow then refills the region, and the cycle repeats. The time dilation seen by the observer blurs these cycles into a near steady continuum, yet the underlying growth remains bursty, with each event adding stars preferentially to the central region and pushing metals and energy into the halo. Over several such cycles, the stellar mass increases by factors of a few, while the half-light radius grows modestly, as new stars form slightly farther out in gas that cools at larger radii, and as dynamical heating from repeated clump migration thickens the distribution. Angular momentum enters through both channels. Smooth inflow carries the net spin of the feeding filament, while mergers supply stochastic kicks that change orientation and magnitude. In a small gas-rich system, the gas can shed angular momentum through torques with clumps and through gravitational instabilities that drive inflow moving material inward and feeding central star formation. This transport helps maintain compactness, despite the accretion of net spin, because angular momentum is redistributed inside the galaxy faster than it accumulates in the outskirts. Clumps that form at a few hundred light-years migrate inward through dynamical friction, and torques delivering their mass to the inner 100 light-years and building a high central surface density. As this happens, a bulge-like component can begin to assemble from the superposition of many short-lived clumps, even while the outer structure remains irregular. The size increase that does occur arises from stars formed in the wake of expanding feedback-driven shells, and from gas that cools at slightly larger radii as the halo mass increases and the virial temperature rises. The net result is a slow size growth relative to mass growth, which places the system along the steep size-redshift relation measured across samples. The circumgalactic medium facilitates or hinders this growth depending on its thermal state. If repeated bursts heat a large fraction of the halo volume to temperatures where cooling times are long, inflow slows and growth pauses until the gas radiates and condenses. If outflows exit through narrow channels and leave most of the volume near the virial temperature or below filaments, continue to deliver fuel efficiently. GN-Z11's blue continuum and high specific star formation rate suggest the latter regime feedback is present but not volume filling, and the halo remains a reservoir rather than a shield. As metallicity rises through local enrichment, cooling in the halo accelerates at some temperatures, increasing the chance that recycled material condenses and returns. This accelerates mass build-up further and begins to lay the groundwork for a more extended stellar component at later times. Mergers add complexity to kinematics and structure without erasing compactness at once. Minor companions deposit stars in shells and streams that at current resolution blend into the compact light profile, their gas shocks and mixes igniting new clumps and adding to the irregularity of the inner few hundred light-years. Occasional more equal mass events at this epoch can double the stellar mass quickly and thicken the central structure, but even then the deepening potential and high gas fractions allow the remnant to remain compact and to regrow a dense core. The key difference from later epochs is the dominance of gas with high gas content Dissipation allows inflowing material to sink to small radii and form stars there while in lower gas fractions. At later times, mergers tend to build outer envelopes more efficiently. Thus, the same process that will eventually make large galaxies also keeps early ones small in size. Gas-rich assembly funnels mass inward. The likely path from a system like GN-Z11 to descendants at later times follows this logic. Over the next few 100 million years in the galaxy's frame, continued inflow and frequent minor mergers will grow stellar mass and raise metallicity. Clumps will migrate inward and coalesce into a central bulge-like component. Feedback will enrich and stir the halo, while rising dust content will increase attenuation and strengthen coupling between radiation and gas. As the halo mass crosses thresholds where stable virial shocks form at large, radii inflow will begin to heat upon entry, and cooling will proceed first at the edges of the halo, rather than all the way to the core. This transition lengthens supply times and promotes the formation of a more extended gaseous disk that can settle as turbulence declines and star formation spreads outward. The compact core will remain as the dense center of the larger system, and the half-light radius will grow faster as star formation shifts to larger radii and as minor mergers deposit stars in the outskirts. Over a few billion years, the descendant could resemble a small present-day bulge plus disk system, or after further merging the central region of a larger spiral or lenticular galaxy. The chemical record will track this growth. Low metallicity now will give way to rising heavy element abundances as successive generations of stars enrich the gas. Dust-to-gas ratios will climb, reddening continua and increasing far-infrared output that at lower redshifts becomes observable against a cooler cosmic background. Nebular line ratios will migrate along sequences that reflect higher metallicity and lower ionization parameter as star formation spreads and stellar populations age. The circumgalactic medium will accumulate metals in extended halos that later appear as absorption systems in quasar sightlines, at intermediate redshift carrying the memory of early outflows far from the stellar body. The high specific star formation rate of the present phase will decline as gas fractions fall and as the balance of inflow and outflow shifts with halo mass, yet within the compact core elevated surface densities may persist, feeding a slow build of central mass that anchors the future morphology. Kinematics will also evolve. Velocity dispersion set by turbulence and clump motions will give way to a more ordered rotation as disks settle. The central few hundred light-years will remain hot in a dynamical sense, supported by random motions, as a bulge forms from coalesced clumps. Rotation curves will extend to larger radii as mass and size grow, and the balance between rotation and dispersion will tilt toward rotation in the outer disk, while staying dispersion-dominated in the core. If a central massive black hole seeds and grows its feedback, may later add an energetic channel that further regulates star formation by heating or expelling gas from the inner regions. But at the epoch of GN-Z11, the stellar processes dominate the ledger. Environment beyond the halo adds slow modulation. If GN-Z11 resides in an overdense region, that will become a group interactions and mergers will be more frequent and mass growth will be faster. If it lies in an average field, smooth accretion will play a larger role, and the transition to extended structure may be more gradual. In both cases, the early compact phase leaves a durable imprint, a dense center that persists inside the later larger body. Observations of compact quiescent galaxies at intermediate redshifts suggest a path where early dense cores after rapid growth quench and later build extended envelopes through dry mergers. In gas-rich paths, compact cores continue forming stars while disks develop around them. GN-Z11's current blue continuum and active state place it on the star-forming branch of this diagram at the earliest time accessible to present instruments. Linking this growth path to populations at later times relies on matching integrated properties across epochs, stellar mass size, surface density, metallicity, and star formation rate. When these are evolved forward under simple physically motivated rules, compact blue low-mass systems at extreme redshift can populate the progenitor space of massive galaxies a few billion years later. Not all such systems follow the same route. Some quench early and remain compact. Others build extended disks, and others merge into still larger systems. The diversity emerges from differences in merger histories, inflow rates, and halo masses. Yet the initial conditions set by systems like GN-Z11 are common starting points in models and surveys. Throughout this growth, the observational imprint changes slowly with redshift. The hydrogen break that now selects the galaxy moves to shorter observed wavelengths as the universe ages, and resonant lines that are now suppressed become more visible when local neutral fractions drop. Far infrared emission from dust strengthens as dust masses rise, and the background cools, providing a complementary view of obscured star formation. Spatially resolved imaging begins to separate clumps and gradients, revealing the internal structure that is now blurred into a compact light profile. Kinematic maps resolve rotation and dispersion, and metal line absorption against background sources traces the expanding memory in the halo. Each of these views at later times will look back to initial conditions like those now read in GN-Z11, and will connect the compact blue phase to mature forms. In the calm register kept here, the message of growth is that early galaxies gain mass quickly, while remaining small because inflow is strong. Gas is abundant, feedback is powerful yet channeled, and mergers are gas-rich. Size grows slowly at first because dissipation funnels material inward, and because outer regions are not yet dominant in star formation. Later, as halos deepen and heat inflow as dust and metals rise, and as turbulence declines, structure spreads outward, and the compact core becomes the dense heart of a larger system. GN-Z11 stands as a measured instance at the beginning of this path. Its compact light blue continuum and high specific star formation rate describe the opening lines of a long evolution whose next chapters are already written in the physics of inflow feedback and merging that operate without change as the universe expands and cools. GN-Z11 does not form in isolation. It sits within the early scaffold of the cosmic web, where matter gathers along filaments that intersect in small knots, which will later become groups and clusters. At this epoch, the contrast between filaments and voids is still rising, yet the bias of young galaxies toward overdense regions is already in place. A compact bright system at extreme redshift is therefore more likely to reside near a filament crossroad than in a deep underdensity. The surrounding field, sampled by deep imaging, contains faint sources whose colours hint at similar redshifts, though small number statistics and noise make firm associations rare. Even without a rich census, the logic of structure formation provides context dark matter. Halos of the mass implied for GN-Z11 form earliest, where fluctuations are slightly higher than average, and those same places seed early gatherings of neighbours. In such a setting, smooth inflow along one or two dominant streams maintains a steady gas supply, while smaller halos ride those streams toward the same node and become minor companions or future mergers. The geometry of filaments matters for how gas arrives and for how feedback escapes. Filaments present narrow, dense lanes through which cold gas can reach the halo center efficiently when halo masses are still modest and when shocks at the virial boundary are weak or absent. If two filaments feed the halo from different directions, angular momentum delivered to the center can vary in time, keeping rotation axes unstable and promoting inflow through gravitational torques. Outflows, by contrast, tend to seek paths of least resistance, which are often perpendicular to the planes of incoming streams. This anisotropy allows inflow and outflow to coexist without immediate cancellation. Fresh gas arrives in sheets, while hot enriched gas vents through chimneys that cut between them. The circumgalactic medium described earlier therefore inherits a directional structure from the Webb itself, a structure that can raise the time-averaged escape fraction of ionizing photons by opening stable low-density corridors even as other directions remain blocked. Clustering at these times also shapes reionization locally. Ionized regions around early galaxies expand into a patchy, partly neutral intergalactic medium, where sources cluster their bubbles, overlap sooner, and create extended zones of low neutral fraction. Where sources are sparse, bubbles remain isolated and small. GN-Z. 11's brightness and compactness suggest a vigorous photon budget for its size. A few neighbours doing the same would knit together a local pocket of ionised gas. The continuum break observed in spectra carries an imprint of this environment. A deep, sharp drop with a smooth redwood slope is consistent with significant neutral gas along the line of sight outside the immediate vicinity of the galaxy. A red damping wing that extends farther implies even more neutral gas. If the wing is weak and a faint resonant line appears, a local ionized zone may already be present. Either way, the Webb-based picture explains why different sight lines through the early universe yield different line strengths at similar redshifts topology. Not a single global number sets the transmission. Estimating the halo mass of GN-Z11 within this environment uses abundance matching and simple dynamical arguments. The luminosity places the system on the bright tail of the early ultraviolet luminosity function. Matching number densities to simulated halo distributions assigns a characteristic halo mass that is small compared with present-day large spirals, but large enough to sustain continuous inflow and to retain gas against the weakest feedback. The compact half-light radius and the high surface density of star formation suggest a central potential, where circular speeds are a few tens to perhaps 100 kilometers per second. Such values are consistent with halos that are still assembling rapidly and that double their mass in a few 100 million years. Within these halos, the freefall time from the virial radius to the centre is short enough that gas can cycle through inflow star formation and outflow many times before the universe ages by even a small fraction. Cosmic variance limits how far a single field can be generalized. A deep pointing that contains a bright compact source at extreme redshift might sample an overdense region, while another field of equal depth might contain none. Surveys mitigate this by tiling many independent sightlines and by combining results. GN-Z11's role in this approach is to anchor the bright end at the highest accessible redshift, with concrete measurements of size, slope and redshift. Even one such anchor constrains the tail of models that otherwise rely on extrapolation. If more examples at similar brightness and redshift appear in other fields, as observations accumulate, then clustering of bright systems will become a measurable statistic rather than an inference. Until then, the environmental reading remains that a bright compact system likely sits in a node of the Webb where early assembly is accelerated. The early Webb also sets boundary conditions for gas thermodynamics. Filaments at these times are narrow and cold relative to the halos they feed. Their densities are high enough that cooling proceeds quickly once gas is compressed in the inner halo, yet they are also susceptible to heating by nearby outflows and by the rising ultraviolet background from ionization. As ionization progresses, the pressure of the intergalactic medium rises slightly, which can slow infall into the smallest halos but has little effect on those at the mass scale relevant here. For GN-Z11, this means that inflow continues largely unhindered along filaments, while the ambient medium outside the filaments becomes more ionized and slightly warmer. The result is an environment where the contrast between supply lanes and surrounding gas grows sharpening anisotropy in both accretion and escape. Neighbour interactions leave subtle signatures in compact galaxies that current imaging only hints at. Tidal features from minor mergers at these redshifts are small and low in surface brightness, easily lost to cosmological dimming. Their dynamical effect, however, is not small. A passing satellite can torque the central gas trigger a burst and then dissolve into the core on short timescales. Repeated minor events build up central density, without creating extended stellar halos immediately a pattern that aligns with the very small measured sizes. More equal mass encounters are rarer but not absent. When they occur, they may thicken the central mass and reset angular momentum. Even after such an encounter, high gas fractions and strong dissipation allow the remnant to remain compact and to re-establish clumpy star formation. The environment therefore accelerates growth without quickly erasing compactness. Large-scale radiation fields feed back onto small galaxies as well. As the ultraviolet background rises, photoheating suppresses gas accretion into the very smallest halos and can reduce cooling efficiency, at the edges of larger halos. At the mass scale relevant to GN-Z11, this suppression is modest during the epoch when the galaxy is observed. Internally generated radiation remains the dominant agent in shaping the interstellar and circumgalactic media. Externally, the background reduces neutral hydrogen in low-density regions, potentially increasing the transmission of resonant lines along specific sight lines once local bubbles have grown. In this way, environment and internal properties conspire to set which spectral features survive at a given time and position. Future association of GN-Z11 with neighbours will depend on deeper, wider imaging and on multi-object spectroscopy that can confirm redshift of faint candidates in the same field. If a handful of systems at similar redshift cluster within a few tens of thousands of light-years in projection, then a proto-group interpretation gains strength. The combined photon budgets of those systems would support a larger ionized zone and might explain weaker damping wings or the presence of faint lines. If neighbours are absent to deeper limits, then the system represents an efficient, relatively isolated early builder, and its bubble must be driven largely by its own output. Either outcome is informative about the range of environments that host the first bright galaxies. Interpreting sizes within the Webb context also clarifies why the size-redshift relation is so steep. At early times, the supply of low angular momentum gas dominates, because inflow rides narrow filaments, and because gravitational torques within gas-rich clumpy systems remove angular momentum efficiently. Star formation therefore traces dense central regions and half-light radii remain small. As time passes, halos gain angular momentum and mass virial shocks stabilize at larger radii, and inflow brings higher angular momentum gas that settles farther out. Clumps migrate inward and build dense centers, while outer disks grow from fresher accretion. GN-Z11 sits near the start of this sequence. Its compact light does not imply a lack of angular momentum in the halo. It reflects the dominance of dissipation and torque at early stages. Metal transport into the environment follows the same filaments and vents. Outflows enriched by the first supernovae travel along low-density channels and mix with filament sheaths, seeding them with trace-heavy elements. This early mixing raises metallicity in gas that will later accrete increasing cooling rates and altering cloud chemistry in the next rounds of star formation. The pattern of enrichment is anisotropic, at first richer, along former vent directions and poorer elsewhere, but turbulence in the circumgalactic medium and continued minor mergers smooth the pattern over hundreds of millions of years. At intermediate redshifts, absorption systems seen toward background beacons will carry these early fingerprints as weak metal lines spread over wide velocity ranges. The cosmic web further modulates the probability of strong lensing magnification. While the line of sight toward GN-Z11 shows no clear signs of strong lensing by massive foreground clusters, weak magnification by large-scale structure remains possible. Filaments and sheets along the path can alter fluxes at the tens of % level without producing obvious distortions. Such magnification would shift inferred intrinsic luminosities and star formation rates slightly downward, but would not change classification or environment. Surveys fold this possibility into error budgets by comparing number counts across fields and by modelling the expected distribution of magnifications. For a single object, the safest course is to report ranges that include the possibility of mild brightening. Within this networked view, GN-Z11's role is straightforward. It is a compact, efficient node that draws gas along one or more filaments, converts a significant fraction into massive stars on short timescales, enriches and stirs its halo through feedback, and likely shares its neighbourhood with a small number of similar builders. Its photons assist in clearing the local intergalactic medium, while its metals seed nearby gas for future cooling. Its compactness follows from the dominance of low angular momentum inflow, and from rapid internal torque and dissipation. Its future size growth will follow from the gradual shift toward higher angular momentum accretion, and from the accumulation of minor mergers that deposit stars at larger radii. The Webb supplies the galaxy transforms and the environment records. This context does not add exotic mechanisms to the ledger. It situates standard processes within the geometry and statistics of the early universe. Filaments deliver vents, expel neighbors, modulate, and the patchy ionization field filters light on its way to present instruments. The measured properties of GN-Z11, blue continuum, small size, low dust, low metallicity, high specific star formation rate slot naturally into this scheme. The next step, keeping the same pace, turns to the longer arc that connects such systems to present-day galaxies. How repeated cycles of inflow feedback and merging transform compact early builders into diverse descendants, and how present observations at later times carry the memory of these first visible chapters. Connecting GN-Z11 to descendants at later times begins with quantities that persist through growth: central surface density, specific star formation, rate metallicity size, and the ratio of rotation to dispersion. Compact early builders start with high, central surface densities inside radii of a few hundred to a few thousand light-years, high specific star formation rates, low metallicity and dispersion, dominated kinematics in their cores. As halos gain mass and angular momentum inflow arrives with higher specific angular momentum, turbulence weakens and disks spread. The compact core remains as a dense center, while the half-light radius increases as stars form at larger radii and as minor mergers deposit stars into the outskirts. The central surface density stays elevated even as size grows, because clumps that formed early migrated inward and coalesced, and because later inflow continues to feed the inner region through torques. Observations at intermediate redshift reveal small dense galaxies that have little ongoing star formation and sizes of order a kiloparsec. These systems likely descend from compact builders that exhausted or expelled gas in their centers, while later growth added an envelope through dry mergers that brought stars rather than gas. Other paths remain star-forming and build extended disks around dense centers, with rotation overtaking dispersion in the outer regions while the core stays hot. GN-Z11's placement at the start of this fork is set by its blue continuum and compact light. It holds the seed of a dense center, and stands in the phase when gas is abundant and star formation rapid for its mass, so both descendant families remain accessible under different accretion and feedback histories. Dust growth traces one line of this transformation. Early low metallicity populations produce little dust and ultraviolet slopes are blue. As supernovae and later asymptotic giant branch stars return heavy elements, grains form and grow in dense clouds. Radiation couples more strongly to dusty gas, raising radiation pressure feedback and altering outflow geometry. Attenuation rises and obscured star formation becomes a larger share of the total. At later epochs, far infrared emission from dust warms above the cosmic background by a wide margin and becomes an efficient tracer of star formation hidden from ultraviolet surveys. A system that began with a blue slope like GN-Z11 will under sustained star formation develop a redder continuum and stronger far infrared output. The fraction of ionizing photons that escape declines as dust grows, and as neutral gas covers more sightlines, which shifts the way such galaxies contribute to the ionizing background. These shifts do not erase the compact core, they change how its growth appears in different bands and how efficiently radiation leaves. Metallicity records another line. Low metallicity in early phases limits cooling at some temperatures, prolonging hot bubbles and aiding breakout. Rising metallicity enhances cooling in the circumgalactic medium, increases the rate at which recycled gas returns, and enriches clumps that form later. Nebular line ratios migrate along sequences that chart this change, moving from high ionization parameter and low metal content toward more moderate conditions as stellar populations age and as gas fractions decline. The interstellar medium becomes more stratified with metal-rich inner regions and gradients that flatten only as mixing proceeds or as mergers stir the disk. Absorbers in the halos of descendants at intermediate redshifts carry the memory of early enrichment as weak metal lines spread over large velocities a signature of outflows that began in compact phases. The core's metallicity climbs faster than that of the outskirts, building gradients that later observations can measure and link back to early assembly. Kinematics shift as structure spreads. In the compact phase, high gas fractions and strong feedback keep velocity dispersions high. Rotation can be present even at early times, but ordered motion competes with turbulence and clump migration. As halos grow and disks extend, rotation curves emerge and become measured by ordered gas and young stars at kiloparsec scales, while the central few hundred light-years remain dispersion-dominated. Bar features can arise as disks settle, driving gas inward and feeding central star formation that maintains the density of the core. Minor mergers heat the disk and thicken it, while gas inflow cools and reforms the thin component. Over billions of years, the balance between heating and cooling determines whether a galaxy settles into a thin extended disk around a dense center, or transitions toward a thicker system with lower star formation. GN-Z11's core, if preserved, will contribute to the high central velocity dispersions of descendants and to the compact bulge components seen later. Star formation histories evolve from bursty to more continuous as inflow steadies and as turbulence declines, then to quenched in systems where gas supply falls below the level needed to sustain clouds. Quenching can arise when halos become massive enough to support stable virial shocks that prevent cold streams from reaching the core, when feedback heats the circumgalactic medium to long cooling times, or when central engines grow and inject energy that clears or heats gas. At the earliest times, stellar processes dominate. Central black hole growth may be present, but remains a minor energy source compared with clustered feedback. As mass rises, black holes can accrete more steadily, and their outflows or radiation can join the ledger that governs gas. In descendants of compact builders, this channel can promote early quenching of the core while disks continue to build, or it can maintain a low star formation state once gas fractions drop. The presence of a dense early core shortens the time for a central engine to reach regimes where feedback matters, by raising central densities and by feeding the nucleus through torques and clump migration. Size growth at fixed mass is modest during the earliest phase because stars form where gas is densest, and because minor mergers deposit stars on orbits that at first are not much larger than the core. Later, as outer disks become the main sites of star formation, and as dry mergers add stars to the outskirts, size grows faster. This two-regime behavior explains the steep size redshift relation at early times, and its flattening later. GN-Z11 sits before the transition in the regime of slow size growth and rapid mass growth. As it moves forward in time, its half-light radius will increase as the outer light builds. If it quenches, early size can still grow through minor dry mergers that puff up the envelope while leaving the core denser route that yields compact quiescent systems at intermediate redshift. If it remains star-forming size, growth will be driven by inside-out disk building, with color gradients that move from very blue to moderately blue as dust and age gradients develop. Angular momentum plays through both regimes. Early inflow along narrow filaments delivers low angular momentum gas that sinks toward the center, while torques and instabilities redistribute what little angular momentum is present. Later, inflow carries higher angular momentum that settles at larger radii, a sequence that builds extended disks and reduces the need for strong internal transport. The memory of early low angular momentum phases remains in dense centers, with high stellar surface densities, and in bars or pseudo-bulges that preserve inward transport histories. GN-Z11's compactness is the outward sign of that initial condition. Its future disk, if it forms, will remember the later condition through rotation speeds and scale length that match halo growth and filament geometry at lower redshift. The circumgalactic medium continues to mediate growth. Early outflows enrich and stir the halo, setting up conditions that later favor condensation at intermediate radii and return flows that fuel disks. As metals accumulate, cooling becomes more efficient and cloud formation proceeds more readily, in the halo producing a cycle of condensation and rain that feeds the outer disk without requiring direct stream penetration to the core. The balance between halo heating by feedback and halo cooling by radiation sets whether this precipitation cycle runs steadily. At halo masses above a threshold, precipitation can be suppressed and quenching follows. Below it, cycling continues. The descendants of compact builders trace both outcomes depending on mass environment and duty cycles of feedback channels. GN-Z11's mass scale and early phase place it below the threshold, at first in the regime where precipitation and inflow sustain growth. Observational links across time rely on consistent measures. Stellar mass must be derived with compatible assumptions about star formation history and initial mass function. Sizes must be measured in rest frame bands that track similar components, correcting for band shifting with redshift. Surface densities must adopt the same definitions. When these controls are applied, samples align compact blue systems at extreme redshift evolve into denser than average centers at intermediate redshift surrounded by growing envelopes that lift half-light radii. Some compact centers quench and become the cause of early quiescent galaxies. Others remain active and become bulges of larger spirals. Metallicity gradients measured later match enrichment histories expected from inside-out growth and from outflow recycling. Far infrared detections rise as dust masses climb, tracking the shift from unobscured to partly obscured star formation. The role of environment remains as a slow background. Systems in overdense regions undergo more mergers and quench earlier on average. Systems in average fields grow disks for longer. Stripping and harassment in groups and clusters at later times can remove gas from outer disks and halt star formation, preserving dense centers while dimming outskirts. The initial compact phase leaves cores resilient to such external processes because high binding energy shields inner stars. GN-Z11's eventual environment will color its path, yet the early imprint of compactness will remain in central densities that exceed those of a later formed stars at larger radii. Tracing the memory into present-day galaxies reveals signatures in stellar populations and dynamics. High central alpha element ratios point to rapid early star formation, consistent with compact phases where bursts are common and timescales short. Age gradients that place older stars in the center and younger stars in the disk match inside-out growth. Velocity dispersion peaks toward the center, record the survival of early hot components. Thick disks and flares reflect minor merger heating of growing disks. Extended metal line absorbers around present galaxies recall early outflows that seeded halos. Each of these observables read together ties present forms to compact beginnings. The path from compact blue builder to mature descendant remains diverse in detail but simple in structure. Gas supply governs star formation, feedback regulates pace and structure, halo growth sets geometry and timescales, and mergers add steps. The same processes that write GN-Z11's present properties continue with altered weights, as mass metallicity and dust increase. No new physics is required. The ledger evolves as terms change coefficients. The early compact core remains as a persistent term visible later as a dense center that anchors rotation and sets the inner potential. Placed back into the steady narrative, GN-Z11 stands as a measured instance at the start of this arc. Its compact size, blue slope, low metallicity, and high specific star formation rate define initial conditions that under common growth rules lead to dense cores at intermediate times and to a range of mature galaxies at late times. The next section keeps the same tone and turns to the practical limits of observation at the edge of the current reach and to how future instruments will reduce uncertainties on redshift metallicity, kinematics and environment, tightening the connections between early builders and their later descendants without changing the underlying sequence. Observation at the edge where GN-Z11 resides is limited by physics, by instruments, and by selection. Physics sets the stage with surface brightness dimming that steepens with redshift stretching wavelengths and thinning photon rates, until only long integrations in the infrared can lift a source above the background. Instruments add their own ceilings through detector noise point spread functions that blend compact structure and calibration steps that must remove small drifts without subtracting faint signal. Selection prunes the sky by colour cuts that demand a strong hydrogen break, and by morphology filters that reject point sources, yet these same choices can miss unusual objects whose spectra or shapes diverge from simple templates. The result is a census that is careful rather than complete, and a set of measurements that emphasize integrated quantities over resolved structure. GN-Z11 enters this regime as a compact blue high redshift galaxy, whose detection rests on repeated imaging and on a spectroscopic continuum break measured at the limit where counts are low and backgrounds high. Photometric redshifts, which compare observed colours to model spectra across filters, remain the first tool for discovery at these depths. Their strengths are reach and efficiency, their limits are degeneracies between dust age and redshift, and correlations in noise that can inflate apparent significance if not modelled. Spectroscopic confirmation resolves these degeneracies, but spectroscopy at extreme redshift faces its own barriers. Slits admit only a small sky area and can miss light if placement is imperfect. Slitless modes risk overlap and contamination. Resolution must be balanced against throughput because a higher dispersion spreads few photons thinly. At the epoch of GN-Z11, even the strongest hydrogen line can be suppressed by a partly neutral medium, leaving the continuum break as the primary anchor. That break is robust when it appears in multiple instruments at the same wavelength, yet its exact position carries an error set by resolution and by the signal-to-noise of the red continuum. These limits are practical rather than conceptual. They ask for time, for careful calibrations, and for methods that propagate uncertainties without optimism. Angular resolution shapes what can be learned about structure. Compact galaxies at extreme redshift have half-light radii of a few hundred to a few thousand light-years, which map onto angles that challenge even space telescopes. The point spread function blurs clumps into a smooth core, erases small gradients, and blends light from neighbouring sources at the faintest levels. Deconvolution recovers only what the data can support. Overreach amplifies noise into false structure. Morphological K-corrections add a second layer of care because the same filter samples different rest frame wavelengths at different redshifts. A fair comparison of sizes across time therefore uses bands that track similar stellar populations or applies corrections that model how profiles change with wavelength. For GN-Z11, the available filters probe rest frame ultraviolet, where star-forming clumps dominate, and older stars contribute little. Sizes measured here are not the same as sizes measured in rest frame optical light at later times. This is not a flaw. It is a boundary condition that must be carried when linking cores across epochs. Completeness in surveys at this edge depends on background levels that change with zodiacal light, and on detector behaviour that evolves with time. Dither patterns and mosaics mitigate pixel sensitivity variations and persistence, but residuals remain. Source extraction tolerates spurious peaks when thresholds are low, yet strict thresholds miss real marginal detections. Teams address this by injecting synthetic sources into raw frames, recovering them with the same pipelines, and mapping completeness and purity as functions of magnitude, size, and colour. GN-Z11 survives these checks at the bright compact end for its epoch, where completeness is higher than for diffuse sources, and purity is well characterized. Fainter analogues push into regions where recovery drops, and where fields with higher backgrounds become effectively shallower, increasing cosmic variance and widening error bars on number counts. Foregrounds and line confusion complicate spectra. Emission from the telescope and the sky sets a background that varies with wavelength leaving windows, where sensitivities are highest, and troughs where deep integration gains little. Lines from oxygen or carbon at extreme redshift can land near residual backgrounds, or within regions where calibration is most uncertain, lowering detection probability. Even when a feature is present at the correct position, identification must weigh the possibility of an interloper from a lower redshift line falling by chance into the same pixel. The guard against this is consistency, a break at the right wavelength, a continuum slope that matches a young low metallicity population, and the absence of flux blue ward of the break in multiple filters. GN-Z11 meets these guards, and remaining line ambiguities are acknowledged rather than ignored. Time dilation smooths variability in the observer frame. Light curves that would reveal bursts or fading in the galaxy frame are stretched by factors of several to many, making near-term changes undetectable and moving studies of variability to populations rather than to individuals. Stacking spectra and images from multiple sources with similar properties becomes a tool to beat down noise and to extract average features like weak metal lines or mean sizes. The cost is loss of individuality. The gain is precision on ensemble properties. GN-Z11 contributes to such stacks as an anchor at the bright end. Its inclusion strengthens average constraints. Its specific numbers remain bounded by its own data. Gravitational lensing offers both opportunity and caution. Strong lensing by massive clusters can magnify very faint small sources into view, stretching them into arcs that reveal structure at scales otherwise inaccessible. Weak lensing by large-scale structure perturbs fluxes by modest amounts without obvious image distortions. For GN-Z11, no strong lensing is apparent. Weak magnification remains possible. Surveys account for this by modelling expected magnification distributions along random lines of sight, and by folding the resulting ranges into errors on intrinsic luminosity and star formation rate. Lensing also provides a program for the future. Targeted observations of carefully modelled lensing clusters can push the detection threshold to fainter intrinsic luminosities and to smaller sizes, sampling the population that may dominate ionizing photon budgets. Future instruments and surveys will reduce each of these limits. Wider and deeper imaging in the infrared will map more independent fields to uniform depths, lowering cosmic variance and improving the bright end tail where GN-Z11 sits. Space telescopes with large fields and stable point spread functions will deliver mosaics that capture both rare bright systems and the diffuse backgrounds against which they sit. Spectrographs with higher throughput at low resolution will place continuum edges with smaller errors and will search more efficiently for weak lines between background features. On the ground, extremely large telescopes with adaptive optics will resolve the shapes of compact galaxies at rest frame ultraviolet and optical wavelengths, translating current integrated measurements into spatially resolved profiles that reveal clumps, gradients, and the beginnings of rotation. Millimeter facilities will detect faint dust and molecular gas even against a warmer cosmic background, at high redshift constraining obscured star formation and gas masses directly, rather than by inference from ultraviolet slopes. Together, these advances will shrink uncertainties on dust metallicity, kinematics, and mass. New windows on the surrounding medium will also open. Tomographic maps of neutral hydrogen through radio arrays that target the long wavelength signature of hydrogen will trace the progress of reionization across the sky. Cross-correlating these maps with catalogues of extreme redshift galaxies will reveal whether bright compact sources sit within ionized bubbles earlier than average, and how their photons carve corridors through the patchy medium. Deep multi-object spectroscopy will confirm redshifts for faint neighbours in the same fields, turning hints of association into measured protogroups, and transforming the environmental context from plausible to direct. Surveys that combine space and ground facilities will tie stellar-like gas dust and metals together, for the same objects replacing model-dependent inferences with joint fits to many observed components. Calibration will remain as important as apertures. Detector response drifts flat field structure, and point spread function wings must be measured and tracked over years. Absolute flux scales must be tied to standard stars observed in the same modes as science exposures. Wavelength scales must be checked against internal lamps and sky features. Small errors have large consequences when spectra rest on a single continuum edge. Teams already use overlapping filters, repeated visits, and independent reductions to safeguard against hidden biases. Future programs will formalize these checks across surveys, ensuring that photometric redshifts built from one dataset translate cleanly to spectra taken by another. Selection functions will broaden as methods diversify. Color cuts designed for a single spectral template will give way to probabilistic selections that incorporate a range of continua dust contents and line strengths. Machine-aided classifiers will rank candidates by the full shape of their spectral energy distributions, rather than by simple two-color planes, while still subject to human review that scrutinizes outliers. These changes will catch rare systems that current cuts miss, and will quantify how many sources fall outside standard boxes. The payoff will be a more complete picture of the early galaxy population, in which GN-Z11 occupies a well-measured niche, rather than a singular point. Linking early builders to later descendants will tighten as anchor points multiply. More bright compact galaxies at extreme redshift will fix the bright end of the luminosity function with smaller variants. Deeper lensed surveys will extend the faint end toward the regime where most ionizing photons may originate. Intermediate redshift studies will fill gaps in size and metallicity evolution with spatially resolved data. At lower redshift, observations of circumgalactic halos in absorption will trace metals that early outflows deposited. Each layer will reduce reliance on extrapolation, and each will make the path from compact blue phases to mature forms an empirical corridor rather than a sequence of models. Within this forward view, the present reading of GN-Z11 remains steady. The continuum edge fixes an extreme redshift within modest bounds. The blue slope points to little dust and to young massive stars. The compact size reflects a small stellar body at high surface density. The lack of strong resonant emission aligns with a patchy partly neutral medium, or with internal geometry that traps resonant photons. Star formation rates derived from ultraviolet light remain high for the galaxy's small mass, with ranges that reflect uncertainties in the initial mass function. Metallicity sits well below solar values with faint lines, and continuum fits pointing to only a few enrichment cycles. Kinematics are unresolved in detail but consistent with modest turbulence and with outflows that do not fill the halo. None of these statements leans on fragile steps. Each is the overlap of multiple measurements and the careful transport of errors through pipeline and model. The practical message is not that present observations are thin, it is that they are honest. They deliver what the universe and instruments allow, and they make clear what future facilities will add. A compact blue extreme redshift galaxy, such as GN-Z11, is measured most securely by its continuum and size. Lines, dust, and kinematics come next with growing instruments. Environment will sharpen as neighbours are confirmed and as maps of neutral gas are overlaid. In every case, the quantities that matter for linking early builders to later forms, mass, size, star formation, rate, metallicity, and escape fractions will be stated with narrower bands over time, and the broad picture will hold. Early galaxies are small, efficient low in metals and dust, and embedded in dense webs that feed them rapidly, while a patchy medium filters their light. With limits and prospects now set in the same measured tone, the path can continue inward, to the concluding layers that gather the full field into one continuous account, from the edge of observation to the light's travel to the instruments that register it to the young environment and stellar populations to feedback, and the circumgalactic medium to spectral signatures and growth, to the Webb and descendants, and then to a short wind down that returns the scene to quiet shapes without changing the ledger that the data write. The light from GN-Z11 does not simply record a distant object. It also carries the imprint of its journey through an expanding universe. Each photon leaves the surface of a star when the universe is only a few 100 million years old and travels through a medium that stretches space itself. The wavelength of that photon elongates in proportion to the expansion, so by the time it reaches current detectors, its energy has shifted from ultraviolet to infrared. This redshift transforms young hot starlight into a faint glow on sensor arrays cooled nearly to absolute zero. The same process that redshifts the light also dilates time, slowing all intrinsic variation from the source by factors of more than 10. What observers see is a time-smeared composite of many cycles of star formation and feedback compressed into a single steady view. The path the photon takes is not a straight line in the Euclidean sense, but a geodesic bent by gravity along every scale it encounters. It leaves the compact galaxy, crosses the circumgalactic medium, and enters the intergalactic web, where it passes through filaments of mostly hydrogen that are partly ionized by the first generations of galaxies. Along the way, it accumulates tiny absorptions at discrete redshifts, where neutral hydrogen remains imprinting a forest of lines at shorter wavelengths than those observed. Most of this structure is lost in noise at extreme redshift, yet its collective effect shapes the smoothness of the break that identifies the galaxy. Each photon continues through the cosmic web, crossing voids, grazing clusters, and feeling minute deflections by the gravitational potentials of intervening halos. Weak lensing magnifies some paths slightly, and demagnifies others, a random field that averages to near unity but scatters fluxes by small amounts. At last the photon enters the local universe, passes through the halo of the Milky Way, through thin clouds of interstellar gas and dust, through the atmosphere of a telescope, or the vacuum of space, and finally lands on a detector pixel where its energy becomes an electron. Calibration turns these electrons into counts into fluxes, and fluxes into the physical quantities used throughout this description. Each step requires corrections for bias, dark current, flat field, cosmic rays, and pointing drift. The data are co-added, cleaned, and fitted to models that account for the instrument response, and for the finite size of the point spread function. From these processed images and spectra come the colours, slopes, and breaks that define the galaxy. The process is mechanical and statistical, yet the care behind it sets the quality of the scientific picture. The faint continuum that defines GN-Z11's redshift rests on hundreds of thousands of such photon events, each one transformed by these steps from raw arrival to calibrated measure. The final uncertainty in redshift or flux encodes both the shot noise of small numbers and the systematic control achieved by calibration. The redshift itself measures not velocity in the simple sense, but the ratio of the scale factor of the universe now to that when the photon left. The number is large because space has expanded by more than 10 times in linear size since emission. The distance in light years that corresponds to this redshift depends on the cosmological parameters that describe expansion and matter content. When integrated through a standard model, the travel time emerges as over 13 billion years, meaning the light left when the universe was less than 5% of its current age. The come-oving distance, the distance if the universe were frozen today, is larger, still extending more than 30 billion light-years. These numbers translate the abstract notion of redshift into temporal and spatial measures that situate GN-Z11 near the frontier of what can be seen. The intervening medium modifies the light beyond mere stretching. Absorption by residual neutral hydrogen in the intergalactic medium sculpts the sharp edge at the hydrogen threshold. Scattering by small concentrations of dust in intervening galaxies can redden spectra slightly, though at this wavelength range the effect is small. Gravitational time delay through dense regions adds tiny offsets in arrival time among photons that left simultaneously but travelled through different potentials, yet these are orders of magnitude below detection. The overall effect of the journey is to preserve the continuum shape, while attenuating the flux and sharpening the break. It is remarkable that such integrity survives across cosmic distances. It is this stability that allows astrophysicists to use the same physical interpretations developed for nearby star-forming regions to explain the faint glow at the universe's edge. Each generation of telescopes extends this reach by collecting more photons and by lowering noise. The Hubble Space Telescope first registered GN-Z11 as a faint source in deep infrared imaging, its colour indicating a strong dropout shortward of a specific band. The James Webb Space Telescope then extended coverage to longer wavelengths, confirming the break and refining the slope with higher sensitivity. ground-based observatories supply context through wide fields that map structure on larger scales. The combination of these instruments forms a chain that links the faint ancient light to a modern understanding of galaxies as physical systems obeying the same laws as their nearer descendants. Future observatories already planned will expand both depth and area, replacing small fields with panoramic views that capture hundreds of similar systems across the sky, allowing statistical comparisons that today rest on single examples. The photons themselves do not change, only the ability to detect them improves. Noise decreases, calibration steadies, and models become more exact. With each step, the uncertainties that accompany GN-Z11's measured properties narrow. Star formation rates, dust contents, and masses all presently known within wide ranges will sharpen. Metallicity estimates will move from limits to values, and velocity dispersions will shift from guesses to measurements. Yet even as detail grows, the fundamental picture already set by current light will stand small size low metallicity, high specific star formation rate, and a position in time when the universe is young and the Webb is dense. Beyond GN-Z11 lies darkness not yet pierced by observation. Light from sources at still higher redshift is stretched beyond current detectors, absorbed by the increasing neutral fraction of hydrogen, or too faint to distinguish from noise. The edge is not fixed, it recedes as sensitivity rises. The next generation of instruments will push this boundary closer to the moment when the first galaxy is assembled from primordial gas, and when the first stars ignited in isolation. Each newly observed source will extend the chronology of formation backward by small steps, reducing the gap between direct observation and the epoch of recombination from which the cosmic microwave background arises. In this way, the chain of evidence will connect the smooth early universe seen in microwaves to the structured one seen in infrared, closing the loop between theory and observation, with continuous data rather than inference. At this stage, the description of GN-Z11 is already part of that chain. It is one link among a growing sequence of galaxies that mark the timeline of assembly. Its faint red-shifted light defines a point where the first substantial systems have taken shape, where star formation is efficient, but still dominated by short-lived massive stars, and where dust and metals are beginning to appear. The journey of its photons from emission to detection completes the outermost arc of this narrative from formation, inside a dense filament of the early Webb through the expanding medium of the universe, to the detectors that record them today. Each element of that arc, the environment, the stars, the gas, the feedback, the growth and the observation, fits into one continuous physical story governed by well-tested laws. With the photon path and its interpretation now set, the next section keeping the same measured pace, will turn to the internal composition once more. The detailed interplay of baryons and dark matter inside the halo, how potential wells and energy budgets hold structure together against expansion, and how these invisible frameworks sustain the visible galaxy that instruments like Hubble and Webb detect at the threshold of the observable universe. The framework that holds GN-Z11 together is dominated by dark matter. This invisible mass outweighs ordinary baryonic matter by about a factor of 5 when measured on large scales, and even within the compact halo of a young galaxy, it sets the gravitational potential that governs gas inflow, rotation and stability. The baryons, gas, dust stars and plasma respond to this potential, well cooling and condensing in its centre, while dark matter remains collisionless and extended. The shape of the halo determines how rapidly gas can fall inward, and how much energy feedback must apply to resist collapse. In the case of GN-Z11, where stellar feedback is strong and gas fractions are high, equilibrium is achieved when the pressure from feedback balances the pull of gravity in the inner few hundred light years. This balance maintains the observed compact size and high surface density without runaway collapse or total dispersal. Dark matter halos at this epoch are small compared with those of modern galaxies, but their densities are higher because the universe itself is denser. The typical mean density inside the virial radius scales with the background density of the universe so halos forming early have deep potential wells relative to their size. This depth allows them to retain gas heated by supernovae and radiation, even while allowing some fraction to vent outward. The escape velocity from the center of a halo hosting GN-Z11 may reach a few hundred kilometers per second, sufficient to confine much of the ejected material to the circumgalactic medium and ensure recycling over tens of millions of years. Within this potential, gas cools through radiation of atomic lines, loses energy, and settles into a rotationally supported structure. The angular momentum of this gas derives from tidal torques accumulated during collapse, and from later mergers that add stochastic spin. In compact galaxies, turbulence and gravitational instabilities redistribute angular momentum inward-feeding central regions, while maintaining irregular shapes rather than smooth disks. The interplay of dark and baryonic matter can be expressed as an energy budget. Gravitational energy released during and full converts to thermal and kinetic energy in gas, which radiates away at rates set by temperature and metallicity. Feedback from stars replenishes thermal and kinetic energy, while radiation from young stars adds pressure. The balance among these channels defines the internal state of the interstellar medium. If cooling dominates, gas collapses into dense clumps and star formation accelerates. If feedback dominates, gas disperses and star formation pauses. In GN-Z11, the two are nearly in balance on average, yielding a continuous but fluctuating rate that produces a steady blue continuum in the observer frame. This self-regulation is typical of small active galaxies at early times and requires no special tuning beyond the general properties of cooling and feedback. Magnetic fields, though weak, provide additional structure. They thread the gas and tie charged particles to field lines, altering transport of heat and momentum. In dense clumps, fields can be amplified by turbulence and by rotation, reaching strength sufficient to influence cloud fragmentation and to guide outflows. Cosmic rays produced in supernova remnants add further pressure along field lines, aiding in the lifting of gas from the disk into the halo. These processes are not directly observable in GN-Z11, but simulations calibrated at lower redshift suggest their presence is inevitable wherever star formation proceeds. The smoothness of the observed continuum and the moderate escape of ionizing photons are both consistent with a medium that is turbulent but magnetized, porous but confined. The gravitational potential of dark matter also shapes rotation curves. If GN-Z11 were to be resolved kinematically, its rotation speed would likely rise steeply in the inner few hundred light-years before flattening a pattern seen in simulations of early compact systems. The ratio of rotation velocity to velocity dispersion would be modest, perhaps 1 or 2, indicating that pressure support from turbulence contributes significantly to equilibrium. As the system gains mass, and as gas fractions decline, rotation will dominate more strongly and disks will settle. At the current epoch of observation, however, the interplay of random and ordered motion keeps the structure spheroidal in appearance even though net spin is present. This dynamical state explains why early galaxies appear as bright knots. Without extended disks, turbulence washes out thin structures and feedback thickens the gas layer, while star formation proceeds throughout the volume rather than in a plane. The inner halo transitions smoothly into the intergalactic environment without a sharp edge. The virial radius defines a region where the mean density is about 200 times the background value, but pressure and temperature gradients extend farther. Inflow from filaments enters the halo continuously, while outflows leak through low-density corridors. Shocks form where opposing flows meet, converting kinetic energy into heat. The virial temperature of a halo hosting GN-Z11 reaches tens of thousands of degrees Celsius, hot enough to ionize hydrogen, but low enough that gas can cool rapidly through line emission. As the halo grows, its virial temperature will rise, and at some threshold a stable shock will form near the virial radius, slowing inflow and creating a hot atmosphere that cools only by radiation over long time scales. At this transition, star formation efficiency declines, marking the shift from the compact bursty phase to a more extended regulated phase, typical of mature galaxies. Dark matter also sets clustering bias. Halos of the mass that host GN-Z11 trace regions where density fluctuations are above average. Their clustering relative to the underlying matter distribution reveals how early structures trace the seeds of later clusters and superclusters. Statistical analyses of fields containing such galaxies show that their distribution already hints at the large-scale web, familiar at later times, filaments, nodes, and voids arranged in a pattern determined by the growth of dark matter fluctuations. The light from GN-Z11 thus marks not only a single object, but also a node in a growing network of structures whose mass will one day collapse into clusters containing thousands of galaxies. The baryonic fraction within the halo, the ratio of ordinary matter to total mass, may be below the cosmic mean because some gas has been expelled by feedback. Yet the gravitational potential ensures that a significant portion remains bound. Recycling of expelled material raises the effective retention as gas lifted to the halo cools and falls back. Over long intervals, this cyclical flow enriches the halo and maintains star formation, without requiring continuous external inflow at the same rate. The fraction of gas converted into stars at any moment remains small compared with the total baryonic mass, preserving a reservoir for future growth. The dark matter itself evolves quietly, merging with nearby halos and deepening the potential well. Its density profile remains roughly self-similar, steep in the center, shallow in the outskirts. Baryonic contraction can steepen the inner profile slightly, but feedback-induced fluctuations can counteract this by heating dark matter through potential variations, a process known as core formation. The balance of these effects depends on the amplitude and frequency of starburst-driven outflows. In GN-Z11, where bursts occur on short timescales, repeated potential fluctuations could soften the central cusp of dark matter, producing a shallower core. Later, as the system gains mass and turbulence declines, contraction may resume. These internal adjustments remain hidden to current observation, but are captured in models that link feedback to dark matter structure. Ultimately, the interplay of dark and baryonic matter defines the visible morphology and the invisible architecture that supports it. The compact body of GN-Z11 is the luminous trace of a deeper, more massive halo extending far beyond what telescopes can resolve. Within this halo, gas cycles between inflow star formation and outflow regulated by gravity and feedback. The equilibrium that results is neither static nor chaotic, but dynamic, maintaining near constancy of size and luminosity over intervals of tens of millions of years in the galaxy frame while mass and metallicity climb slowly. The visible stars mark where energy balance, cooling, and gravity intersect inside the larger dark scaffold. Understanding this framework completes the inward journey from the outer web to the inner core. The next and final section before the wind down will hold this structure steady and trace with the same slow clarity how the passage of time and the expansion of space carry systems like GN-Z11 forward, how their light fades, how their descendants form, and how the boundary of observation shifts with every new photon caught in the long night of the universe. The framework that holds GN-Z11 together is dominated by dark matter. This invisible mass outweighs ordinary baryonic matter by about a factor of 5 when measured on large scales, and even within the compact halo of a young galaxy, it sets the gravitational potential that governs gas inflow rotation and stability. The baryons, gas dust stars, and plasma respond to this potential well cooling and condensing in its center, while dark matter remains collisionless and extended. The shape of the halo determines how rapidly gas can fall inward and how much energy feedback must supply to resist collapse. In the case of GN-Z11, where stellar feedback is strong and gas fractions are high, equilibrium is achieved when the pressure from feedback balances the pull of gravity in the inner few hundred light years. This balance maintains the observed compact size and high surface density without runaway collapse or total dispersal. Dark matter halos at this epoch are small compared with those of modern galaxies, but their densities are higher because the universe itself is denser. The typical mean density inside the virial radius scales with the background density of the universe, so halos forming early have deep potential wells relative to their size. This depth allows them to retain gas heated by supernovae and radiation, even while allowing some fraction to vent outward. The escape velocity from the centre of a halo hosting GN-Z11 may reach a few hundred kilometers per second, sufficient to confine much of the ejected material to the circumgalactic medium and ensure recycling over tens of millions of years. Within this potential, gas cools through radiation of atomic lines, loses energy, and settles into a rotationally supported structure. The angular momentum of this gas derives from tidal torques, accumulated during collapse, and from later mergers that add stochastic spin. In compact galaxies, turbulence and gravitational instabilities redistribute angular momentum inward, feeding central regions while maintaining irregular shapes rather than smooth disks. The interplay of dark and baryonic matter can be expressed as an energy budget. Gravitational energy released during infall converts to thermal and kinetic energy in gas, which radiates away at rates set by temperature and metallicity. Feedback from stars replenishes thermal and kinetic energy, while radiation from young stars adds pressure. The balance among these channels defines the internal state of the interstellar medium. If cooling dominates, gas collapses into dense clumps and star formation accelerates. If feedback dominates, gas disperses and star formation pauses. In GN-Z11, the two are nearly in balance on average, yielding a continuous but fluctuating rate that produces a steady blue continuum in the observer frame. This self-regulation is typical of small active galaxies at early times, and requires no special tuning beyond the general properties of cooling and feedback. Magnetic fields, though weak, provide additional structure. They thread the gas and tie charged particles to field lines, altering transport of heat and momentum. In dense clumps, fields can be amplified by turbulence and by rotation, reaching strength sufficient to influence cloud fragmentation and to guide outflows. Cosmic rays produced in supernova remnants add further pressure along field lines, aiding in the lifting of gas from the disk into the halo. These processes are not directly observable in GN-Z11, but simulations calibrated at lower redshift suggest their presence is inevitable wherever star formation proceeds. The smoothness of the observed continuum and the moderate escape of ionizing photons are both consistent with a medium that is turbulent but magnetized, porous but confined. The gravitational potential of dark matter also shapes rotation curves. If GN-Z11 were to be resolved kinematically, its rotation speed would likely rise steeply in the inner few hundred light-years before flattening, a pattern seen in simulations of early compact systems. The ratio of rotation velocity to velocity dispersion would be modest, perhaps 1 or 2, indicating that pressure support from turbulence contributes significantly to equilibrium. As the system gains mass, and as gas fractions decline, rotation will dominate more strongly, and disks will settle. At the current epoch of observation, however, the interplay of random and ordered motion keeps the structure spheroidal in appearance, even though net spin is present. This dynamical state explains why early galaxies appear as bright knots, without extended disks. Turbulence washes out thin structures and feedback thickens the gas layer, while star formation proceeds throughout the volume rather than in a plane. The inner halo transitions smoothly into the intergalactic environment without a sharp edge. The virial radius defines a region where the mean density is about 200 times the background value, but pressure and temperature gradients extend farther. Inflow from filaments enters the halo continuously, while outflows leak through low-density corridors. Shocks form where opposing flows meet, converting kinetic energy into heat. The virial temperature of a halo hosting GN-Z11 reaches tens of thousands of degrees Celsius, hot enough to ionize hydrogen, but low enough that gas can cool rapidly through line emission. As the halo grows, its virial temperature will rise, and at some threshold a stable shock will form near the virial radius, slowing inflow and creating a hot atmosphere that cools only by radiation over long timescales. At this transition, star formation efficiency declines, marking the shift from the compact bursty phase to a more extended regulated phase typical of mature galaxies. Dark matter also sets clustering bias. Halos of the mass that host GN-Z11 trace regions where density fluctuations are above average. Their clustering relative to the underlying matter distribution reveals how early structures trace the seeds of later clusters and superclusters. Statistical analyses of fields containing such galaxies show that their distribution already hints at the large-scale Webb familiar. At later times, filaments, nodes, and voids arranged in a pattern determined by the growth of dark matter fluctuations. The light from GN-Z11 thus marks not only a single object, but also a node in a growing network of structures whose mass will one day collapse into clusters containing thousands of galaxies. The baryonic fraction within the halo, the ratio of ordinary matter to total mass, may be below the cosmic mean, because some gas has been expelled by feedback. Yet the gravitational potential ensures that a significant portion remains bound. Recycling of expelled material raises the effective retention, as gas lifted to the halo cools and falls back. Over long intervals, this cyclical flow enriches the halo and maintains star formation without requiring continuous external inflow at the same rate. The fraction of gas converted into stars at any moment remains small compared with the total baryonic mass, preserving a reservoir for future growth. The dark matter itself evolves quietly, merging with nearby halos and deepening the potential well. Its density profile remains roughly self-similar, steep in the center, shallow in the outskirts. Baryonic contraction can steepen the inner profile slightly, but feedback-induced fluctuations can counteract this by heating dark matter through potential variations, a process known as core formation. The balance of these effects depends on the amplitude and frequency of starburst-driven outflows. In GN-Z11, where bursts occur on short timescales, repeated potential fluctuations could soften the central cusp of dark matter, producing a shallower core. Later, as the system gains mass and turbulence declines, contraction may resume. These internal adjustments remain hidden to current observation, but are captured in models that link feedback to dark matter structure. Ultimately, the interplay of dark and baryonic matter defines the visible morphology and the invisible architecture that supports it. The compact body of GN-Z11 is the luminous trace of a deeper, more massive halo extending far beyond what telescopes can resolve. Within this halo, gas cycles between inflow star formation and outflow regulated by gravity and feedback. The equilibrium that results is neither static nor chaotic, but dynamic, maintaining near constancy of size and luminosity over intervals of tens of millions of years in the galaxy frame while mass and metallicity climb slowly. The visible stars mark where energy balance, cooling, and gravity intersect inside the larger dark scaffold. Understanding this framework completes the inward journey from the outer web to the inner core. The next and final section before the wind down will hold this structure steady and trace with the same slow clarity. How the passage of time and the expansion of space carry systems like GN-Z11 forward, how their light fades, how their descendants form, and how the boundary of observation shifts with every new photon caught in the long night of the universe. Time carries GN-Z11 forward while the expansion of space stretches its light and lowers the background density that feeds its halo. In the galaxy's own frame, tens of millions of years pass as bursts of star formation alternate with quieter intervals. Clumps form, migrate inward, and dissolve into the dense center. Metals accumulate in gas and stars, raising cooling efficiencies in the circumgalactic medium and shortening the return time for recycled material. Dust grows in dense clouds and in supernova ejecta, increasing attenuation at short wavelengths and strengthening far infrared emission once the cosmic background cools sufficiently. The compact body remains the principal site of star formation at first because angular momentum is transported inward rapidly by torques and instabilities. Later, as the halo mass rises and virial shocks stabilize at larger radii, accretion brings higher angular momentum gas that settles farther out. Star formation spreads into a young disk while the core preserves high-velocity dispersion and high stellar surface density. The half-light radius grows slowly at first, and then more rapidly, as the outer light builds, tracing the familiar inside-out growth seen at later epochs. The ionization state of the surrounding medium evolves in step. Early patchy reionization gives way to a steadily rising ultraviolet background, as more galaxies contribute photons. Ionized bubbles around clustered sources expand and join, reducing the neutral fraction of hydrogen in low-density regions. Resonant hydrogen emission that was weak or absent at the highest redshift can slip through more easily along some sightlines as local opacity declines. The damping wing on the red side of the hydrogen break fades. Continuum slopes redden gradually as dust increases, though the most intense star formation remains brightest in the rest frame ultraviolet, until obscuration becomes strong. The escape fraction of ionizing photons drops as porous channels close more quickly, and as dust absorbs more high-energy light inside the galaxy. The net contribution of a single system to the global ionizing budget falls, while the accumulated population of similar systems at slightly lower redshift sustains the background. Mass assembly continues through smooth inflow and frequent minor mergers. The halo doubles in mass on timescales of a few 100 million years, adding depth to the potential and lifting the virial temperature. Gas that once streamed cold to the core now shocks at the edge of the halo more often, then cools and condenses inward on timescales longer than a single burst cycle. The circumgalactic medium thickens into a quasi-stable atmosphere with pressure gradients that regulate precipitation. Feedback from clustered star formation heats parts of this atmosphere and drives turbulence that delays condensation in some regions, while leaving others cool enough to form clouds. The balance settles into a cycle in which dense clumps rain toward the disk, form stars and are partially expelled again, as winds enriching the halo further. Metals spread along filament sheaths, and outflow cones raising the baseline metallicity of future inflow and of neighbouring halos that share the same web. Over longer intervals, minor mergers deliver stars to the outskirts and increase scale lengths, while rare major encounters thicken the body and may reset angular momentum. In all paths, the early compact core remains as a durable high-density centre that anchors dynamics and preserves the memory of the first phases. Stellar populations age. Short-lived massive stars that once dominated the ultraviolet continuum die quickly and leave behind remnants and chemical yields. Intermediate mass stars emerge as significant contributors to the light on timescales of hundreds of millions of years, adding to the near-ultraviolet and optical continuum and shaping any age breaks that become measurable at later epochs. Low-mass stars long-lived and dim-store most of the stellar mass and will dominate the light in the red and infrared at very late times. The integrated spectrum evolves from very blue to moderately blue, and then to a mix that depends on how long strong star formation persists. If gas supply holds and dispersal is modest, the system builds a disk and remains on the star-forming main sequence with gradually declining specific star formation rate. If feedback and environment combine to halt supply, or to heat the circumgalactic medium above rapid cooling, the system quenches in its core first and moves to a low star formation state, while size grows through dry mergers. In both outcomes, the early compact core remains a distinct structural component in the descendant. Kinematics move from turbulence dominated to rotation supported outside the core. Velocity dispersions drop as gas fractions decline and as feedback becomes less explosive relative to the deeper potential. Ordered rotation appears clearly at kiloparsec scales when disks settle, while the central few hundred light-years retain high dispersions from old clumps and from thickened stellar orbits. Bars can form as disks grow, driving gas inward and renewing central star formation that maintains high densities. If a central massive black hole seeds and grows, its influence remains secondary at first compared with stellar processes, but can rise later to regulate residual gas in the core through winds or radiation. At the epoch of observation, the light does not require this channel. The ledger is balanced by stars' gas turbulence and gravity alone. Observationally, the path from extreme redshift to intermediate times replaces the single strong hydrogen break with a richer suite of features. As redshift decreases, rest frame optical lines move into accessible bands, providing precise metallicities, ionization parameters, and kinematics. Dust emission emerges against a cooler cosmic background and reveals the obscured part of star formation. Spatial resolution improves in physical units, as angular diameter distance evolves, separating clumps and gradients within bodies that previously appeared as smooth knots. Weak gravitational lensing and deep imaging map environments over wider fields, connecting individual galaxies to filaments and nodes that later become groups. Absorption studies against bright background sources detect metals in extended halos, tying chemical memory to the outflows that began during the compact phase. Each step narrows the inference space allowed at extreme redshift and confirms in detail what the early continuum implied: small size, high specific star formation, rate low metallicity, and efficient coupling between feedback and a dense porous medium. The limit set by current instruments recedes with time. Deeper imaging finds fainter galaxies and extends the luminosity function to the regime where the bulk of ionizing photons may arise. Targeted lensing surveys use clusters as natural telescopes to resolve intrinsically tiny systems. High-throughput spectrographs place continuum edges and weak lines with smaller errors and unveil velocities where only fluxes were known. Tomographic maps of long-wavelength hydrogen emission chart the topology of reionization and correlate ionized regions with the locations of compact star-forming galaxies, turning an indirect environment into a measured one. As these tools mature, uncertainty bands on star formation, rates, metallicities, sizes, escape fractions, and masses tighten. The central picture remains: early galaxies are compact blue, low in metals and dust, and embedded in dense filaments that feed them rapidly, while a patchy medium filters their light. The memory of GN-Z11's phase persists in present-day galaxies. Dense centers with high alpha element ratios, steep central velocity dispersion peaks, and old stellar ages point back to fast early assembly. Outer disks with younger ages and lower dispersions record later extended growth. Metal line absorbers at large radii trace early outflows that seeded halos with heavy elements, long before extended stellar bodies formed. The diversity of present morphologies, spirals, lenticulars, ellipticals, arises from variations in merger history, environment, and halo mass. Yet a common thread runs through many a compact efficient beginning that left a durable core. The faint red-shifted continuum of GN-Z11 marks such a beginning captured close to its time of occurrence. The same physical rules apply throughout. Gravity governs collapse and sets clocks. Cooling and heating regulate the interstellar and circumgalactic media. Feedback from stars couples radiation and momentum to gas. Angular momentum channels where disks form and how clumps migrate. Dark matter provides the scaffold within which all of this unfolds. No special mechanism appears only at the edge. Only the weights of familiar terms change with density, metallicity, and mass. This continuity is why the early light can be read with confidence. The same processes that shape nearby galaxies operate in nascent ones, under conditions of lower metal content, higher gas fraction, and higher background density. Placed at the end of this long arc, the description returns to the data that ground it. The redshift is set by a continuum break measured consistently across instruments. The blue slope constrains dust and supports young, massive stars in a low metallicity medium. The compact size fixes a small physical scale for the stellar body. Weak or absent resonant emission aligns with a partly neutral environment or with geometry that traps resonant photons. Star formation rate, stellar mass, and metallicity remain ranges with explicit caveats tied to the initial mass function and to hidden older light. Kinematics are implied rather than resolved, but fit within the expected mix of turbulence and rotation for compact gas-rich systems. Environment is hinted at by neighbouring candidates and by theory, and awaits deeper confirmation. Each element fits with the others in a single consistent picture. The observable boundary will move, but the record of this phase will remain as a benchmark. Future detections at even higher redshift will approach the first instances of sustained star formation. Deeper samples at similar redshift will fill in the faint population that likely dominates photon budgets. Spatially resolved spectroscopy will map internal gradients and flows. Joint analyses that combine stellar light, ionized gas molecular gas dust and metal absorbers will turn present integrated statements into detailed histories. Against that expanding canvas, GN-Z11 will hold its role as an early anchor that links the smooth microwave sky to the clumpy infrared sky, and ties models of structure growth to the first resolved galaxies. With this final layer in place, the continuous path from the outer frame of observation to the inner workings of a compact extreme redshift galaxy is complete. The view begins with faint red light stretched by expansion, passes through instruments that record its steps into a dense early environment where gas cools, quickly follows young massive stars that drive feedback into a porous medium, reads spectral signatures that set metallicity and ionization, tracks growth through inflow and merging inside a web of filaments, and closes with the dark scaffold that supports the visible structure. Time and expansion carry the system forward, but the ledger set by current photons is clear and reproducible. The scene is ready to settle into the brief wind down that restores the quiet with the compact galaxy in place, as one measured instance of how the first generations of stars gather in small halos and begin the long build toward the galaxies of the present day.